Alright, hell yeah. So we have physics, and this is a red problem. You know what I mean? It's kind of like the 3-star. You know what I mean? It's the most difficult. And so what we have here is a rotating Earth, and we got a golfer that's shooting their ball to the south. And for whatever reason, because the Earth is spinning, and then before they hit the ball, that ball is also spinning around the Earth, so it has a tangential velocity. But also that hole is to the south, and it has a faster velocity. So on the trajectory, when that ball hits, it'll be behind the hole. So and it's just one of those where it's just like I have to maybe just do the equations to see how that works out. So anyway. So we have the ball is initially hit with an angle of 48 degrees. So this initial velocity, I'm just going to say velocity initial, has a vertical component. So we have V initial sine 48. Has a horizontal component, V initial cosine 48. And yeah, hell yeah, it goes 285 meters. So there's acceleration of gravity, and we do have to label, hey, this is the positive x direction, this is the positive y direction. So the acceleration of gravity is 9.8 meters per second squared, but it's in the negative y direction. Okay, keep that in mind. There is no, and this is due to a force of g m1 m2 radius of the Earth squared. You know what I mean? Because that is the thing. It's like, hey, if we do have this golf ball, you know what I mean? Is there any forces on it? You know, because else, if it has this initial velocity, it would just go forever in that direction. But no, there is forces on it, and those forces are unbalanced because there is no normal force, you know, underneath it. So we would definitely have a force due to its mass. We have an mg down that's causing it. So if we go to the F equals ma, we've identified that for sure there's going to be forces on that, and there's only going to be one that's in the downward direction. And then so that means that this thing has to be accelerating downward. So what does that mean? It's going to change its velocity. Acceleration is changing velocity, changes time. It's going to change its velocity. So if it had a velocity up, well now it's got a slower velocity until it hits some zero, and then it's going to come back down. All right. So and the simplest thing to do is do acceleration is negative 9.8. So that would be dv dt is negative 9.8. Separate variables. dv is negative 9.8 dt. Integrate, and you got equation for velocity. Negative 9.8 t plus c. This c, so you throw in times 0. Well, guess what? Initial velocity is v sine 48. And then so that's at times 0, negative 9.8 times 0, that's all 0, plus c. So now we know that c is v initial sine 48. So now we got our equation for velocity. It's negative 9.8 t plus v velocity initial sine 48. All right, so now we have an equation for, oh, bummer. This is just the equation for velocity in the y direction. That's what we were doing. I apologize. This is acceleration in the y. So we were trying to find the derivative of the velocity in the y. So this is the equation for velocity in the y. We know the equation for velocity in the x. This is the velocity in the x. Okay, hell yeah. But now we have a third component. Okay, now I see this. So now we have a velocity coming out of the page because this point over here on the Earth is spinning faster. You know what I mean? So if this is up and this is the x direction, so we got the y direction, the x direction, well, guess what? tangential velocity is coming out of the page. You know what I mean? So perfect. Z direction. You know what I mean? And so we have a velocity in the Z direction. So the velocity in the Z direction initial, so we need to figure out what the velocity is. What's the tangential velocity of the Earth? You know, maybe at the equator, and then up here at this So let's take a pause on this, and yeah, just because I want to. And so we need to know that. And I even printed this out. The Earth rotates not in 24 hours. It's 23 hours, 56 minutes, and 4 seconds, alpha t. So you would take that. You would go 23 times 3,600 plus 56 times 60 plus 4.091. And then there you go. And I stored that as alpha t. So this is the time for one revolution. One revolution in 86164. 0.91 seconds. So to get radians per second, so we need our do we need it in radians? Yeah, because we need to find angular velocity, which is radians per second. So you take this, one revolution is 2 pi radians, and so you go 2 pi divided by that, and hell yeah, and I store this in my calculator as W. Okay, so now we so we have that, but check it out. Up here, the angular acceleration is 0. At the equator, the angular acceleration is what we found. So now we need to figure out why the angular acceleration is different here. And so what they did is said, they already gave you at least half the problem, even though it's bizarre that they would even give you that. You know what I mean? But whatever, that's helpful. So we know the radius at the location, radius initial. And we're going to say, hey, radius final is a little bit more. But radius initial is radius of the Earth, and we have that in there, 6.37 times 10 to the 6. And we're going to say that's that times cosine of 35 degrees. Make sure we're in degrees. And sweet. So now we have, what did we find? We found that radius. So cool, we're going to store that as alpha s, rs, and then probably t for this one. Because we know that radius, we know this circumference. And so that's going to be 2 pi, kind of like pi d, but the 2 times the radius is diameter, so, d times pi, or 2 times radius times pi. There you go. So 2 pi r, and there we go. So that's circumference. We're going to store that as alpha c. Other one might store as alpha d. So now this is the distance. So this is the distance in meters, and we want to know meters per second. Well, we're going to divide by the time it takes for one revolution. We have that stored in our. So this is going to be a velocity in the z direction initial of 380.5 meters per second. I'm going to store that as alpha v. Okay. And so that's the initial velocity of the ball. And I guess the problem, and I guess now visually I see it. Air resistance is neglected. The fact that the ball gets shot into the air, it keeps. I mean, there's no acceleration in the z direction. There's no acceleration in the x direction. So hell yeah. But we do have a velocity in the z direction initial, velocity z initial, and but this point, you know what I mean? We kind of have to just treat it in three-dimensional space. You know what I mean? Like just pretend like, hey, this little T box is just floating in the stars, and and then this hole, the green, you know, where the hole is also just kind of floating in the stars. But we do know that these two little islands are connected to each other, but just in a way that says what does it say? Is that this velocity is going to be different. So the velocity of the t, I'm going to call it velocity final, is because it's 280. So we would need to find the angle difference. How would we find that? Well, one, we might want to find the arc length. So there you go. If we found this arc length S, and that was some angle, 35 degrees, then we could do S minus 285 millimeters. So and then from that arc length we could find the angle. And then so how do we do that? I'm going to do it down here. If we have radians, that's going to be that times the radius. That's going to equal something normal, and that's arc length, S. Cool. So initially we have 35 degrees, and we got to convert this to radians. So we go 35 divided by 360 degrees. Degrees cancel, and then 2 pi radians on top. Let's do that. So we have 35 divided by 360 times 2 pi. So we get 0.61 radians, and that's what we'd expect. 1 radian is 60 degrees, so 35 degrees, 0.6, so we're all good there. We're going to store that as the angle, theta, in our calculator. And then the radius. So radians times radius, so we're going to go that times the radius. And then that's our arc length. It's the distance from the equator up to that point. And right now I'm not even going to bother, because I'm just going to subtract 285 with, store it in my calculator. So now we have a new arc length, and then we would want to find the angle of that. So we're just going to go angle is arc length divided by radius. So now we're just going to divide that by the radius. Cool. So we have our new angle. And how does that help us? Okay, because now it says, hey, this distance out to here is going to be this equation. Radius. Oh, and if that's in radians, I got to switch to radians. I'm going to store that as z. But we're going to have alpha r cosine of z. So this is going to give us this new distance. Cool. So we got that. Now how do we get the and I'm going to store that as alpha s, because this is our radius final. It's this circle, so we just know 2s pi, 2 pi r. It is this is that, and then we're going to divide it by that time of divide that by the time of one rotation in a day. Cool. So now that's our new speed. So we have 380.51. I mean, it's the exact same, but we're going to store that as u. So alpha v, alpha u. There's a slight difference. Alpha u is faster. Cool. So this one is faster. This one's going to be u. V, z, final. Hell yeah. So we did it. So we got that component. Now we're going to go back over here, because what we want to do is figure out how long this thing is going to take to fall. And even with our equation right here, did we spell it out? Yeah. So at time 0, we have an initial velocity. It's the vertical component. But at some time, these two are going to equal each other. And what that means is the ball it's not moving up, it's not moving, it's at the top of its game. You know what I mean? And what we know is that's going to be the halfway point. So this time we can solve for it. When these two things are equal, or when velocity of y is 0, so we can go 0 is equal to negative 9.8 t plus vi sine 48. And again, we don't know the initial velocity, of how they want you to find that. but we can at least find the time that happens. And bring this over there and then divide by 9.8. Okay, so now we have that time component. And we know the velocity in the x direction. Where the hell's that? The one with the 285. So velocity. Yeah. Oh, I guess I didn't do the equation. So we said, hey, this velocity is the velocity of this times time is that. So we have. So we're going to have velocity initial cosine 48 times time, which is this, velocity initial sine 48 divided by 9.8 is equal to, but this is equal to at the halfway mark, you know what I mean? I'm kind of doing two things at once because I just want to get this problem hella done. And 285 divided by 2, so this is going to be 142.5. So this is kind of where these components get squared, but at the end of the day, you're going to go velocity initial is equal to, and we can just solve for it. So we're going to multiply that by the 9.8, divide by sine 45. But we got to be in degrees for this one. That's why this problem's 3 stars, because you have to switch from radians to degrees. That'll end you. Okay, and then divide by cosine 48. This still leaves you with the velocity squared, so we got to do the square root of this. And hell yeah, we got a velocity initial of 52.99 meters per second. And then multiply by 2.25, and it's 120 miles per hour. So that's hella fast, but that's hitting a ball. You know what I mean? Yep. That's yep. 120 miles per hour. You know what I mean? That's cool. A golfer can hit something faster than a pitcher can throw a baseball, and that makes sense. So yeah, so that's a check on reality there. And now we know the time, because we know the velocity initial, we can go back and figure out the time for halfway. They probably don't want that. How long is the ball in flight? So we're just going to say the ball's in flight for this times 2. I'm just going to ruin the equation and do this. And that's going to be the time in flight, TF maybe. Okay, so we're going to go, we're going to store this as alpha y, because that was our initial velocity. And so we're going to go 2 alpha y sine 48 divided by 9.8. And so we have a time, oh, no way. Why did that just not work? What? Okay. What equation was I doing? I was saying that this. I was saying velocity initial cosine 48 times time is equal to 142.5. There you go. Cool. And then I already found velocity initial. It's alpha u. No, alpha v, alpha w, alpha y. Alpha y. Cool. So we got alpha y cosine 48. I mean, the time component for things going aerial is got to be like just like 18 seconds. Maybe that is true. No way. I'll have to figure that one out. And then I can do a check on reality pretty easily on that one. But all right, so we're gonna do that, but we got to do 142.5 divided by that. Yeah, hell no. It's time is what? And it, oh shoot. No. This was the time for halfway. This was the time for halfway, 1.786, and then double that. So yeah, you can get kind of, yeah, I'm sorry I did it that way, but 3.572. Cool. Yeah, because anything that goes up and down or throws stuff off cliff, man, 5 seconds is a huge downtime. Alright, so yeah, most things are just within 3 seconds. So, Hell yeah. Okay, so yeah, we have our time component. We're going to store that as alpha q. So that's for A. And B, find the eastward speed of the tree relative to the stars. We did that. That was V final. That was alpha u. Cool. And then by how much does the whole speed exceed that of the tree? Okay, yeah. So it's alpha u minus alpha v. It's alpha v, alpha u minus alpha v. It's 0.01 meters per second. So divided times 1,000. Okay, sweet. So we have 11.9 millimeters per second. You know what I mean? And yeah, 11.9 millimeters. So that's a quarter of an inch. You know what I mean? So yeah, this problem is whoa. But that's every second. That's every second. And then multiplied by q. I mean, I don't know if that's 100% correct. But yeah, we got 42.5 millimeters. And hell yeah, that's about an inch. You know what I mean? Just less than an inch. Okay, so but how much does the whole speed exceed that of the t? During the time the ball is in flight, it moves upward, downward, as well as southward with the projectile motion you studied in Chapter 4. But it also moves eastward with the speed that you found. In Part B. The whole moves to the east at a faster speed, however, pulling ahead of the ball with the relative speed you found in Part C. Cool. And that's the relative speed we just found. The you know what I mean, the 0.0119 meters. Okay, how far to the west is? So they're saying that this Earth rotates to the east. See, even that is just like, does it? Does it? How would I find that just real easy? You know what I mean? Because like let's say the sun is stationary. I mean, well, I know the sun rises in the east and then sets in the west. But if it looks like the sun's moving that way, guess what? The Earth's moving that way. Yeah. So New York City is moving, is trying to chase the sun. It caught it, and then goes past the sun, and then we catch it. Yeah. So yeah, I guess the Earth rotates to the east. That was a pretty good one. All right. So but that's it. So this problem, I spent way too long trying to learn rotational acceleration, and it wasn't even needed for this problem. And so if I do put 2 and 2 together, I'll do this video obviously first, and then it's just 4 hours of trash. It's probably about 3 hours of just, there are some moments, it's like teach how to teach. But anyway, this answer is not in the back of the book, but that's it. So it's the time component, whatever time component it takes, but then yeah, these things are moving at different speeds. It is the same thing with shooting the targets. You know what I mean? So if you're doing like the, you know what I mean, shooting the targets, and you're aiming at we gotta throw a couple more in because I'm aiming at that one. But guess what? These things are moving. You know what I mean? You're not moving. Velocity is 0. That's cool. Just like you need the relative velocity. I mean, these things are moving. This one's moving faster. We can just say this one's moving 0, and this one's moving 0.019 meters per second. Cool. So these things are moving. You aiming right at that. You shot it. It's going to take some time for the bullet to get there, and then you miss the target. So that was that part, and we just figured it out. You're going to have a 42.5 millimeter error if you hit the. You know what I mean? But the crazy thing is, I'm going to look up right now the dimensions of a golf ball and the dimensions of the hole. Because they're saying you missed, and so and this is crazy. You're talking about hole-in-ones where it lands right in the hole. It probably pops out, you know what I mean? But they're probably deep enough to cradle a ball. That does and can happen. All right, catch you on the flip side. All right, we're back, and we got some got some answers. So, size of a golf ball, 42.67 millimeters. This was our error in our shot of 42.5. I mean, so basically that's pretty cool. They kind of made it where, yeah, in this case at 35 degrees. And this is probably going to be the most different. See how they chose this problem? You know, even that is just, you know, kind of an interesting thing, because you're going to have the most change in radius. You know what I mean? Like right here, your radius doesn't change. Well, right here, your radius definitely changes. So maybe actually the max radius changes up here for a given diameter. Yeah, I can't answer that question actually. That's, yep, your radius doesn't change and then changes a lot. Yeah, anyway. But the size of a golf hole is 108. Okay, so yeah, you're... Oh, that's surprising. You know, I guess, yeah, the golf ball, you could put just less than 3 of them. So yeah, golf cup's pretty small. Yeah, 3 golf balls won't fit that way in a golf hole. Yeah, 42.67 times 3. Yeah, you'll be 10 millimeters short to do that. So yeah, that's interesting. Yeah, so you have I guess there you go. You have kind of 3 options to hit the golf tee, and so if you were on one of the options that was on, let's see, and then even just these problems, it's just like how far to the west of the hole does the ball land? Okay, it's because we already said the Earth is rotating. Oh, let's see. Find the eastward speed of the tee. Yeah. So yeah, the Earth is rotating east. Thank goodness. Yeah, the Earth is rotating east, so the ball is going to land to the west. Okay. Even just things like that is just like how do you rack that in your brain and have it make sense? Cool. And then I guess I wanted to end this with just, you know, I think this would have been a good ask. So obviously, if you're hitting at this 285, this radius increased because of the Earth being a sphere, and then 2-dimensionally you can see it as a vertical circle. So sure, so this radius increased. Let's say this radius didn't increase because you were hitting off a higher location. You know what I mean? So now I'm just going to go back, and this is probably just easy. I just want to know, like, what if that hole was at a lower location, or vice versa? What if the tee box was at a higher location? I think that would be more fascinating. Having it doesn't matter. Yeah. Obviously, if the tee box, if this is at a lower location, that's the same visual. Okay. So radius of the Earth is this, and what did we say? The radius. Oh, well, we were saying. Okay, I guess we're going to do the whole thing. So this is radius of the Earth cosine of 35 degrees. And so that's that. And then we're going to say, yeah, that's, so now this is that first radius. So we're going to store that. And did I store these as anything? Alpha C, alpha B, no. So I'm just going to store that as alpha N. Whoops. Okay, so that's that. Now we need to figure out what this radius was. So we need to find that angle again. This is a good one for me to do, though. And we were saying that 35 degrees times 2 pi divided by divided by 306. Whoa, 35 times 2 pi divided by 360 is that 0.6. In radians, radians times radius. So we have radians times radius is this arc length. Radius is the Earth, so times alpha r. So this is the arc length minus 285. So this is the new arc length. So find the angle divided by the alpha r. And this is the new angle. So now we have alpha theta and then alpha z. Yeah, the new angle is alpha z. So there you go. So z is our new angle. Angle final is z, and theta angle initial is theta. Okay, so if we have that new angle, we go alpha r cosine that new angle for that equation that they want, and then we found our new radius. And did I even store the old radius? But I'm going to store this as alpha O, because the other one was stored as alpha n. No, we're way off. All right, slow it down. So we have, that's the radius of the Earth, cosine 30. Oh, yeah, duh. We didn't switch our things to degrees. So alpha z is the new angle. That's angle final. So now we need to go to radians. I'm glad I mentioned that. Alpha r cosine of that new angle. Perfect. So now this stores alpha o. So alpha n, alpha o. And they're different. Yeah, they're actually quite a bit different. So now we're going to go alpha o minus alpha n. 163 feet of elevation drop. Damn, that's actually crazy. I would have not thought that. Hitting a ball 285 meters. So we're gonna take this times I don't know. We can just divide by 3.33, and yeah, it's 49 meters. But yeah, 160 feet of elevation drop. Like, I don't know if there's a course. I'll have to look up. I'm going to see the most elevation drop of a golf course. Alright, and I apologize for calling this feet. A lot of mistakes like that. But anyway, 163 meters, which is 49 feet. No. Oh, wait, what did I say? Holy Toledo. No, it's 163 meters, so times 3.33. Yeah, it's 544 feet. Yeah, my apologies. But that would have to be the elevation change. And I was just like, whoa, that's wild. Now, I feel like that doesn't seem right at all. Because if you were on the equator, I mean, it's going to be just no difference. You know what I mean? 285 feet, you're going to go down like millimeters. I mean, I think for every foot you go down like, you know, very little. Yeah. So I'm gonna redo that one. Alright, hell yeah, we're going to be done with this problem, but you might as well see the way I, you know, kind of check for things, just to make sure we got to check on reality, is, you know, one of the checks that's kind of easy is like, well, if I hit the ball from the North Pole 285 meters this direction, well, obviously my radius right there is nothing, and then my effective radius right there is 285. You know what I mean? So getting a radius of a radius difference of 163, sure, that's a check, because I know down here my radius difference is going to be almost 0. So now we're going to maybe do like we're going to go, you know, 5 degrees, and let's go all the way up to let's go 75 degrees. So we're going to go alpha r cosine 75, and so what this gives us is, it gives us this radius. And what's alpha r? Oh, My bad. We have to switch from radians to degrees, so there you go. So we get that. That is that radius, so we're going to store that as alpha I. And, okay, so now we're going to go, we need to find this arc length for 75 degrees. So we have 75 divided by 360 times 2 pi. This is radians. Radians times radius. So I'm gonna store this as we're gonna store it as alpha v. So alpha v times r. This is our arc length, and then arc length. Oh yeah, we haven't subtracted the. So this is our arc length at our angle of 75. We're going to subtract that 285. This is our new arc length. Divide by the radius. Cool. So now this is our new angle. We're going to store that as alpha u. And then we've got to switch to radians. So we're going to go alpha r cosine, radius of the earth cosine of this new angle, alpha u. Perfect. And then this is going to be alpha j. So we have alpha I, alpha j. It looked very similar. Alpha j minus alpha I. Yes, so up here we would have a difference of 275 meters. It's approaching 285. So now we're going to go down to, I'm curious, should we just go 10 degrees? Alpha r cosine 10, switch to degrees. And so this is the radius, very close to the radius of the Earth, right there. And we're going to store that as alpha d. Cool. We're going to find the arc length. 10 divided by 360 times 2 pi. And the more you get used to that, you can just do 10 divided by 180. 10 divided by 180 times pi. See, I even kind of lose my head about that. It's just 10 divided by 360. And then I just know 360 is 2 pi times 2 pi. But if I knew that 180 is just pi, 10 divided by 180 degrees divided by degrees times pi. Alright, so this is the arc length. We're going to switch to radians. This is the angle. And then so angle times radius, that's arc length, minus 285. This is our new arc length, divided by alpha r. This is our final radius of the ball hit. And so we're going to store that as, might as well store it as t. So we're going to go alpha r cosine t. This is alpha e. So this is our new radius. We went from that to that. They look the same, alpha e minus alpha d. So we do have a difference. We have a difference of 49 meters. So yeah, that's impressive. So even at 10 degrees, you're still going to get a difference of 49 meters. Man, I just wouldn't have thought. Like, for whatever reason, that just sounds wrong. But whatever. Is that if you're really close to the equator and you still hit a ball 285 meters, your elevation drop is 49 meters. You know what I mean? So, yeah. Visually, if the Earth is a circle, a vertical circle, that's what we're saying. You go that direction, and then you got to go that direction. And but that's fair enough, because at 45, at 45 degrees, you go that way. How do they do that? Oh, maybe I'm mistaken. Yeah, what the hell are we doing? Oh, yeah. So at 45, what we're looking at is this radius. So that radius compared to going, starting there, and then hitting the ball there. Well, yeah. I guess. at 45 degrees, there you go. So at 45 degrees, if this is 285, well, you're at a 45 degree angle with the Earth is vertical. So then A and B, A squared plus, so you have 2A squared. And A squared plus B squared, they're going to be the same, is equal to 285. So you're going to have 285 divided by 2, the square root of that, and you're going to have 11. See, but or is that right? No, you're definitely not. At 40, so you're going to have A squared plus B squared is equal to 285 squared. So 285 squared divided by 2, square root of that is 201.5. You know what I mean? So let's do that and be done with it. But yeah, I swear, yeah, when circles get as big as the Earth and you're just like, no, that's the thing I live on. I don't know. It's just kind of an interesting thing. So we're going to go degrees, and we have r cosine 45. So that's going to be, we're going to store that as alpha A. So then we're going to go 45 divided by 360 times 2 pi. Cool, that looks about right. And arc length times alpha r. That's the arc length minus 285. Is that what we're doing? 285. And then divided by r. New arc length, new angle final. So then we're going to go alpha r cosine of that answer of, oh shoot, whoops, yeah, so sorry, so here's our new angle, alpha r cosine of that angle, and it's in radians, and then store that as alpha b, alpha a, alpha b. So alpha b minus alpha a, and we get 201. Hell yeah. Okay, so that's a check on reality, but it's just interesting. I don't know. Yeah, circles are bizarre, but we did it. I thought this was going to be a much harder problem, and so it wasn't. And so, yeah, we are. I don't know. You know, it's interesting. I spent about 3 hours just, you know, trying to go over acceleration of circles, and I don't, you know what I mean? I might just do it. You know what I mean? Might just post that. Might as well. It's a learning process. I'll get better, but and I guess you see it. You know what I mean? If you wanted to stick around for like a 3-hour video after this. But anyway, thanks for joining me for this one. And that's why I just went through it, because this is after just spending 3 hours just trying to, I don't know, just hammer home some things on the acceleration of circles, velocity of circles. But man, my understanding when it comes to the differentiation to get to those equations, that was the hard part. We really struggle. I don't actually learn anything new on that. But we got close. I think. And then we did some practical stuff. So it could be worth hanging around for. Probably not. But thanks for joining me for this. And guess what? That's a video. Alright, hell yeah. So we got physics. And we got a red problem. You know, this is synonymous with 3 stars. And so to solve this, I dig this book. This was from the library. This was Schwamm's Engineering Mechanic Dynamics. And it's hard as hell problems in there, and they're confusing in the way they, I don't know, do the math, but all the math is legit, and it's just fascinating. I learned a lot from it. So the take-home point is that we're going to learn how rotational physics works, you know what I mean? And this looks too complex for me, so we're just going to break it down. Basically, at the end of the day, there's 4 things here. 2 are normal, that one and that one, and then the other 2 are just mysterious. And so what we do, or what I do, is if I was on an island with a tennis ball, mess that up, with a volleyball, you know what I mean, I'd probably just be on an island with a tennis ball. But me, I'd want to know I'd want to know how to do the math from scratch. So, you know what I mean? If I don't have any other textbooks, could I still get there? And that's what we're going to do. So anyway, so the problem here is that we have a golf ball that's hit, and just on a golf course, but there's the Earth right there, and it's hit. Great, it goes up and down, and it was going to do a hole-in-one. That's what they were going to say. But guess what? It's hit south, and this ball, before it leaves the tee, is spinning around this circle of the Earth. Let's say it was at the North Pole. It wouldn't be spinning at all. But when it hits, the tee's over here, let's say, just hugely exaggerated. And the tee's spinning faster. Now, even if you just say that, no light bulb goes on. And I think it's just confusing as hell. You're just like, what? The tee's not going to be, like, if I hit it, if I aim at that tee, it's not going to be, it would be like a carnival ride. I mean, you know, one of those games where you have these targets, you know what I mean? And they're moving this way. And, you know, you got your little rifle or whatever, and you aim at that target. But the second you shoot the bullet, that target ain't there no more. You know what I mean? And so, now I get that. I 100% get that. It's still, it seems like there's a, it seems like there, you know, for whatever reason, my mind's like there should be like continuity. Because it, and so we got to talk about that. You know what I mean? So even just like right now, if I throw a ball up in the air at the North Pole, it's going to come right back down. You know what I mean? We get that. The thing's spinning in a circle, you know. But there is some things that I do know that happen with that ball. Like if I have my ball and I'm on top of the North Pole, me and the ball are spinning. You know what I mean? I think I get that. And you really have to speed up the rotation of the Earth for this to... I mean, the Earth is whooping around. And, okay, so me and the Earth I'm spinning, the ball's spinning. And then when I throw the ball up, well, guess what? The ball is still spinning. You know what I mean? Because even when I'm holding it, the ball is spinning around the North Pole. And the second I throw it up, it's still spinning. And then when it lands, it's still spinning. You know what I mean? But I'm spinning too. So, you know, if I had a basketball and I kind of drew like an X on it and put 1, 2, 3, 4, and then threw it up, when I caught it, it wouldn't change. You know what I mean? So this problem, I think the first visual is like, well, let's say when you throw this, like you're spinning and the ball's spinning, you throw this ball up at the North Pole, but for some reason, the second you leave, the second you throw it up, the Earth, stops rotating. You know what I mean? So, and then, but anyway, yeah. You know, then you know when you catch the ball, it ain't gonna look like that. I get that. So that's what's happening with this golf ball. Where you hit it, it has a velocity like this direction, but so does the tee. The tee's got a faster velocity. So the second that you hit it, so I mean, it's like the relative velocity too. You know what I mean? You got to go back to Einstein and be like, well, pretend like this doesn't have a velocity, and let's get a new sheet of paper. Pretend that you don't have a sideways velocity, but this tee does. You know what I mean? And I'm getting closer. I can be like, okay, I got you there. And so the second that ball hits, well, this tee already moved. So, like, you know what I mean? The tee moved across the ground and just was no longer there. So that's basically the question. And every once in a while it seems like, oh, I could just go do that right now. But then I'm just like, no, I need a deeper understanding. So we're going to go over the rotational physics. So in this Schwamm's book, we have, and this is still too complex for me. I'm sorry, I can't get there 100%. Every time I read it, I get a little bit more, you know, juice out of the equation. And I even learn how to do a derivative. You know what I mean? So what they're saying is that, hey, we have a circle, and this you have like, hey, some sort of mass out in a radius, and we're in radial. Oh, and guess what? But that's it. That's it for that. Now we just want to know, and so here's the distance, and then the vector is that direction. Okay, so perfect. So I get this. So here's your vectors. You know, we're learning on the fly. So this is the vector that shows position. You know what I mean, of that thing, and now we want to know. And so let's say this is a vector of 10, magnitude 10. You know what I mean, 10 whatevers. But guess what? It's in the direction this way. We would make a unit vector of 1. You know what I mean? Because then, even though this is like vector 10, we could just say, hey, this is just 10, but in the direction of vector 1. You know what I mean? So that was pretty horrible. But that's the way vectors work. You know what I mean? Vectors have a magnitude and a direction. But if someone just says, hey, I have a vector of 10, I just don't know what direction it is in. But guess what? Someone says it's, you know what I mean, that way. You know, and they point that direction. Oh yeah, it is kind of bizarre. How the hell do unit vectors work? But anyway, well, we'll get there. So anyway, so to get the velocity, so this component, what they're doing is they're doing, I don't know, I just like it because they're doing, well, you have to take the derivative. You know what I mean? So if this is my radius, I want to know what the change in the radius is. You know what I mean? Maybe change in the radius would cause velocity, and so that's the first thing. So if I'm out here on a radius of whatever 10, and then all of a sudden I'm at 11, okay, it looks like, and so for my mind, I go back to like, I mean, this is I go back to kind of simple things. If I see you at the grocery store, and then later that day I see you at the bar, I can say that you had a velocity at some point that day. You are made out of mass, and I saw you at 2 different locations, and time exists. You know what I mean? And you only need, it seems like you only need 2 of those statements. Like Newtonian mechanics says, if you see a mass at one place, and then you see a mass in a different place, that same mass in a different place, well, there must have been a change in time. You know what I mean? Because we're not in quantum physics where you can be at 2 places. It's not superposition, and I think that's useful. I think actually, you know, like saying that, to be like, whoa, I saw a car here, and then I saw a car here. Well, you already invented the concept of time by saying that. You know what I mean? It comes out in the wash that there had to be, you just have this concept of time. You have to have that concept of time in Newtonian mechanics. So anyway, so yeah, so if you have this radius 10, and then you observe that a little while later it's at 11, well, or just, yeah, well, obviously it was a little while later. And now you have, well, all right, holy Toledo. Sometimes they get a little bit too deep, but yeah. If your radius is getting big, if your radius goes from 10 to 11 to 12 to 13 to 14 to 15, well, it looks like you got velocity. So I don't know how many. I haven't said it very good in any ways, but yeah. And I guess, well, what the hell is, so I guess for also, I mean, it's really important. We should go back to like chapter 1, because I've never liked how velocity and acceleration is taught, but you know, the definition, like it's like the word, the word is in the definition. I mean, or maybe the unit. So we're going to look at velocity. Velocity is change in position, change in time. So there you go. I think that Einstein whole, you know what I mean, whatever, was good. Because, hell, we changed our position, and then we just knew that there had to be a concept of time. And I think that is important. That is important. But there you go. So if you have a change in position, you must have had a change in time, and therefore you have this relationship called change in position, you have velocity. You know what I mean? There you go. And let's say that's all you know. You definitely know velocity for sure. If I saw you at the grocery store, then saw you at the bar, you must have had velocity. Doesn't mean you had acceleration. You know what I mean? I might have saw you at the grocery store and you were plodding along. And you could have been plodding along all day, and then I saw you at your bar, and then I saw you, walking through the bar. You know what I mean? Does not mean you ever had acceleration. You know what I mean? So that's important. Because now we do acceleration. It's change. It's a change in velocity, change in time. And I definitely use this caret. I don't like the derivative. I think every time you put a dv there, you just lose everyone. But, so that's why anytime I see this dv, I know that I can change it to like caret v, and then caret t. And then I know I'm getting like a guesstimate. You know what I mean? The whole like derivative is like, hey, let's take things so microscopic they don't even exist. Well, it's just like, yeah, it's like, well, let's not do that. And then actually just kind of, so this is the world I live in. It's just like, well, let's just see what the velocity changed, and then see what the time changed, and be like, hell yeah. If it took 1 second to get from 11 to 12, well, we had a change. What is velocity? Change in position. Well, we went from 11 to 12. So it's, I mean, and then you got to know, like, you know, you don't want to complicate it too much and get too like, well, change in position is position final, so it's x final minus x initial. But hell yeah, it looks like you went 1. You know what I mean? What was your change in? It looks like you went 1. So there you go. You went 1 and it took 1 second. So it's 1 meter per 1 second. So you went 1 meter per second in that scenario. Hell yeah. Now, there's some also things that I do right off the bat. Let's say we saw this piece of mass right here, and it had a velocity of 0. It wasn't moving. So I see you at the grocery store, and you're just looking for cereal. And then I see you at the bar, but then you're walking through the bar. So even just from those two statements, I know at some point that day you had to have acceleration. Because I saw you not moving, and then I saw you moving. So if you have 0 velocity, that's a constant velocity. You would probably have that 0 velocity, and so even though that seems like a simple thing to say, I just think people don't say that, because then problems are like, oh, well, this thing is now going 10 meters per second. You're like, cool. Was it ever stopped? That's always a question you should ask. Like, was this thing ever stopped? And even if the question is just like, hey, given a velocity. Because you hop in your car, you drive to another town, you're probably going 60 miles per hour once you get on the interstate. And that's pretty constant. You know what I mean? And that's probably the value you'll be using, well, 70 or 80 now, but, with stops and stuff, 60 miles per hour. But anyway, so that's how far, if I said in 1 hour, how far could you go? You go 60 miles. But when you hopped in your car, you were going 0 miles per hour, and then it took you a little while to go 60 miles per hour. And even though that little section wasn't a big part of your trip going 60, it still shows that you had an acceleration. You know what I mean? It took acceleration to get to a constant velocity. And it took acceleration to go from 0 to some speed, and then it took a deceleration to go from accelerating to not accelerating. I mean, yeah. So even let's talk about that concept, because you're just like, well, now you just lost me. But it's just like that should be super intuitive. If I'm not moving, and then later I know that I'm going 60 miles per hour, I'm going to have an acceleration to actually get up to speed. So velocity is 0. Going to have an acceleration to get up to speed. And that requires some acceleration. And that's positive acceleration. That's change in velocity, change in time. And so I'm going to, actually, and this is, I'm going to increase my velocity. Increase velocity. Oh, no. Yeah, I kind of answered my own question. I could always have an increase in velocity. I don't have to have a deceleration. Apologize, you know what I mean? But that's some of the things that you're just like, you're trying to work out in your head to get just more intuitive, so you don't run into those stumbling blocks of like, well, if I do if I do the nitty gritty, hell yeah, I'm changing my velocity, going from 0 to 10 to 20 to 30 to 40 to 50. But I guess in that process to get up to the 60, at no point did I have to like go the other direction. I didn't change my velocity to go slower. At the end of the trip, sure, but for this scenario, we're just trying to take our car from 0 to 60, get on the freeway, and then haul. All right. So now how the hell does that relate to rotational physics? And did we get there? Well, it was just the first one, because the first one is just like, well, hell yeah, I'm just going to hunker down. I want to know rotational physics. And the first one is just really easy. It's just like, well, if you consider this your circle, and this is your radius, and then the next point you're just at a bigger radius, and that's what we're saying. Well, you're moving in a line, but your velocity, I want to say my radius has velocity or something like that. But you have velocity in the radius direction. So there's that. And so it seems like, well, if you took the derivative of if you have a radius and the derivative of it is going to find you your velocity, you know what I mean? Well, it's like, well, that one's the obvious one. Well, I'm just going to have a velocity in the direction of the radius. And so and this is good because they use just, I don't know, they use a unit vector in the radius direction, you know what I mean? So they use terms that are a little complex to even visualize. And then for velocity, well, they definitely say that's the time rate of change. So this r hat is the time rate of change of the position. So if this is the position right here, we're going to go the position r dt. And hopefully I got that right, but it's the change in position, change in time. So yeah, even when you do dr dt, it's like, no, just change in radius, change in time, and it's just like, oh, now I see it. I swear that helps me quite a bit. All right, so but then right here you also have a mysterious component. You have this. Didn't we already solve it? If we have a radius and we want to change the radius, well, we'll just be going that direction, and we have velocity in that direction. We got linear velocity. But well, let's grab a sheet of paper and sit down and see if I can even do what is it called? It's called derivative by parts. Is it derivative by parts? But if you have a product and you're trying to take the derivative of a product, you have to take the first times the derivative of the second plus the second times the derivative of the first. But this scenario is pretty cool because, well, and it's elusive too, because it's not totally spelled out like what the hell each of those means. All right. All right, hell yeah. So let's write this down. So we're doing the first one, man. And this is good. This is better than me trying to figure it out in my spare time, because I think I can get to a greater understanding, real time. So we have a radius, and the radius is a scalar quantity. The radius is a scalar quantity, not a vector quantity. This line indicates a vector quantity of the radius. So that vector quantity of the radius is a unit vector in the radial direction. That's ER. And then with the magnitude R. So that's kind of the first step. And even that is just like, I don't know, I get unit vectors, but then when you're just talking about, man, it feels like I have to go, it feels like this, it'd be so simple. And I just did the first like redid the first 2 chapters of statics, and I love unit vectors, you know what I mean? But man. Anyway. Okay, so but we do the derivative. We take the derivative of this vector with respect to time. Is that what they're doing? They don't even show. They just go right for it. So, and they're calling that velocity, the velocity vector. Okay, so we at least got that. And then they're calling that r dot. Yeah, and we did it. It's derivative of the radius. And I guess the only thing that I messed up is that this is still a vector quantity. All right, so we get what do they do first? They always do this second term. So like they say this first times the derivative of the second. Just pick a term, but like, hey, that term times the derivative of the second. So this doesn't change. Plus this term times the derivative of that term. So we're going to go this term times the derivative of that term. And this doesn't get easier. It gets hella worse. You know what I mean? Because now you're just like, well, I mean, it can make sense to me if I just say it. So this is the radius direction. And if I'm going in the radial direction, so let's draw this again. If I'm going in this direction and I change my direction, and I think I got a good analogy of this. Like, what direction do I go? You know what I mean? Like, well, at the end of the day, you're going to move totally perpendicular. And you'd be like, well, let's say I'm on a walk and I'm going this direction for a long time. And I haven't changed my direction. But then I take a step that way. You know what I mean? And it feels like now I'm going that direction. Well, at the end of the day, to change this direction, it was only the quantity perpendicular. That was the only thing that changed your direction. Because even this little triangle, well, definitely still has a part that goes this way, the way you were going. And the only other part was that way. So that's kind of like a, like obviously this is a statics type example where you're just like, yeah, well, I guess, yeah, if I am going that way now, it has a component this direction and a component that direction. And if I already labeled this direction as like, hey, this is the direction that I was thinking I was going, but all of a sudden I'm moving that way, well, I'm still moving this way. Okay, that's a check mark, but now I'm moving at some distance this way, and that's going to be tangent. And then so cool. So at the end of the day, and I guess the terms is that if this is the unit vector in the radial direction. And then if I am at the radial direction, this is the unit vector in the tangential direction. So at whatever radius I'm at, so we can draw another one. Whatever radius I'm at, here is my unit vector tangentially. And then so, you know what I mean? And if I put the arrow right there, maybe just this small arrow is my unit vector times the radius. And then this radius is like a radius of 3. See how that looks like a unit radius of 3? 1, 2, 3, and there's my unit vector. So cool. So now we just have a unit vector. Oh, and the other thing, they don't use tangential. They use... and I better do this 100% right because they use phi. They don't even use theta. Sometimes I like to use theta, but they're definitely using phi. It's same thing as theta. If I say a theta angle here and this is a change in theta, what they're going to use for this problem is phi. Okay. All right. So cool. So a change. If I'm going along the radius and I change direction, well, it looks like now I'm going in. A unit vector in the phi direction, in the angle direction, or the tangential direction. I'm not going to use this t, but they're going to use phi. But I got to say tangential direction. Yep. Okay, cool. All right, so and then for some reason that gives me velocity, and then we kind of need to figure out why. Why did that give me velocity? By changing, if I was already at this radius, and then I moved tangentially. Let's say I'm just at a radius but stopped, but then I have a I'm moving in the tangential direction. You know what I mean? Or just I see myself here in the radial direction, but then at some other time I see myself just tangential. Well, there must have been a velocity. Like I said, so now it goes back to that, if I saw you at the grocery store, then I saw you at the bar, you must have had a velocity. And then this is going to come up. I've actually never dived into this, just deriving from, I would consider that complicated. Like, I would consider this the most complicated part. Is just like, well, yeah, you're just choosing a radius, and then you're saying we can get velocity out of that by doing the derivative of the product derivative or whatever. But yeah, this term is bizarre. But then, what they do is they, you could read this paragraph, but yeah, and it's confusing to me. But this term doesn't just change. It doesn't just change into that's just the phi direction. Nope, it's the phi. At the end of the day, it's the phi direction times how fast you're moving, your angular velocity, the radians per second. So the angle per second that you're moving in that direction. So this term right off the bat, is that right? Holy Toledo, we got to get this right. E.R. E.R is going to be, yes, is going to be your, and this is phi dot. That's going to be change in phi, change in time. Delta, so we're going to have a change in angle, change in time. Well, that is the definition of angular velocity, omega. All right, hell yeah. And we definitely need to get the next sheet of paper. All right, hell yeah. No, I'm pumped. I'm pumped. I'm excited about this because, yeah, so there you go. There's the omega. And at the end of the day, I mean, holy hell, all this is saying is if we're on a circle, like we could either be moving, getting our radius bigger, and I think that's kind of the more complicated one. But yeah, we could have a velocity in the radial direction, or we could have a velocity in the tangential direction. Well, cool. We all know that the velocity in the tangential direction is r omega. And then now I'll do my axiom, because radians, this is radians per second, but even just like an angle, you're like, what the hell's a radian? Well, you have to divvy up a circle. So anytime you're doing radians, well, divvy up a circle in 6 chunks, and just know that about 60 degrees is 1 radian. You know what I mean? That's the first thing that should pop into your mind working with radians. It's about 6. It's like 57.3 or something. But this is why there's 6 radians in a circle. And there's not. There's 6.28. You know what I mean? But who cares about that 6.28? It's just like a circle is, the circumference is just 3 times the diameter. 3.14, who cares about that 1/4 part? And it's 6.28 because you have 3.14 is just 2 pi. You know what I mean? So that's why, and see how you get the 4's twice and the 1's twice, you get 6.28. And so that's 6.28 radians in a circle. But basically 6. You got 6 radians and 360 degrees. So 360 divided by 6. Every 60 degrees you get 1 radian. Now what the hell is a radian? Well, it's literally the linear distance of the radius. If you had this circle and measured the radius with a string, you would drape that string around this circle and you would find that you would be able to get to there. Do it again, you'd get to there. And about 6 times around, you're basically almost completed the full circle. But you got to go a little bit more. But that's literally the definition of a radian. So my axioms are like, hell, take radians. So let's say you finally found, and we should be like, hey, let's say I have 30 degrees. Shouldn't that be about 0.5 radians? Hell yeah. So how do we convert that? Factor label method. We say, well, we have 30 degrees. Well, I want to know how many degrees are in one full circle. 360. And then get another thing that's similar. I want to know how many radians are in a full circle. Well, we already just defined that as 2 pi radians, or 6.28. So now I could be like, well, I want to get rid of the degrees, and I'm going to say 360 degrees is 6.28 radians. You know what I mean? Or, I mean, you would do it as 2 pi divided by 360 radians per radians in one circle. 360 degrees in one circle. You know what I mean? The one circles cancel, and then the degrees cancel with that. So kind of the factor label method, just real fast for you. But hell yeah. So 30 divided by 360 times 2 pi, and you got 0.52. You know what I mean? So it's not you know, but 1 radian is about, you know, 60 degrees. And, but it's just, it's a, whoa, 30 degrees. Yeah, 1 radian is just a little bit less. That's why if I did 60 degrees, I would get like probably like 1 point, well, let's do it. 60 divided by 360 times 2 pi, and I get 1.04 radians. All right, hell yeah. So, but my axiom is once we know the degrees, and this is how radians are related. Because if we know we have an angle of 57 degrees, or let's just keep it with 60. If we have an angle of 60, we know that this arc length is the same as the radius. So what I say is radians times radius. You know, you're always multiplying by the radius. So radians times the radius. So we have, you know, our angle in radians times the radius is the arc length. And we'll just call that S. And then for velocity, you know what I mean? We're going to say radians per second, which is angular velocity. Radians per second times the radius gives us something normal. You know what I mean? And that's the velocity. And another thing that will come up in this will be angular acceleration, where that's just going to be the radians times the angular. So angular acceleration is radians per second per second. It's the change. It's the change in radians per second. You know what I mean? It is the same thing we did with velocity. Velocity is change in position, change in time. Acceleration is change in velocity, change in time. All right, so yeah, so what do we get? Yeah, we got that term. That was radius times radians per second. Radius times radians, something normal, and then this is velocity. So this is your tangential velocity, and this would be your velocity in the radial direction. So cool. So now we've defined. If you have, in circular coordinates, you can basically have a particle, define where its location is, and it could have 2 components of, you know, it can have a velocity that way and a velocity that way. Alright, so the next part of this gig is to figure out what the accelerations are. And these are our coordinates. I mean, we're in polar coordinates, so we can either have an acceleration in this direction, or we could have an acceleration in that direction. And after we do the derivative, you boil it down to 5 terms pop out. We'll talk about that barely. But then 4 makes sense, and then hopefully we'll get back into what I know. Alright, hell yeah. So took a little break and got a new sheet of paper. And you know what I mean? I just refuse to throw in the towel on this. So we at least deduced from doing the derivative of this, hell yeah, we get a velocity, a radial component of the velocity, got it, and a tangential, like after all that. Okay, so then what they're going to do, I mean, but this part is the most crucial, you know what I mean? It's just like, well, if we do take the product derivative of the, you know, the scalar component of the radius times the unit vector component of the radial direction, you know, where the hell that particle is. So, and then yeah, you get this, you get the change in the unit vector of the radius. So then they do a what the hell is this called? I kind of forget. Anyway, that'll come to me. But yeah, the way they find these values is using vector vectors. And all this was hella confusing to me anyway. It's getting a little bit better. You know what I mean? This is one of the things I just kind of every once in a while pick up and look at. And so I think I got far enough to be like, okay, so what they're basically saying is that we're going to see that particle of mass right there and there. So, booyah, I can even now I'm just going to go through my style. And it's like, hell yeah, that's the person at the grocery store, person at the bar. So I know that they had to have velocity. You know what I mean? So that's basically, by definition, if I saw them two different locations, two different... there must have been a time component, and they must have had a velocity. So now, if I'm defining this as my radius, I can see that, well, they're not along this. I don't find them along this radial path. So that was kind of the first fundamental that I could understand. But I do know where they were here. I can definitely see. That's the first thing I can see. I can definitely see their radius has changed. So then I will know they definitely have a velocity in the radial direction. Cool, but I don't find them along this line. So by definition, you know, I know that they have to have a velocity tangential. So I know they have to have a tangential velocity. Now, and now I think I don't have to do from my perspective. I don't have to do the hand waving now to be like, well, what is tangential velocity? Well, that's angular velocity times something radians times something normal radius. We got radians per second times radius. And then so that's going to be your tangential velocity. But what they're going to say is that the only thing, you know what I mean? Because cool, you would have an equation for velocity in terms of radians per second and radius, but for the most part, if we're just going to define a point as a radius and an angle, then, you know what I mean, this equation for sure should be, hey, the velocity is the change in the radius, got that, satisfied with that, plus, what is omega? Omega is the change of the angle, change in time. Omega, I mean, and that's the first, anytime you get like a term, be like, well, what are the units? Radians per second, you know what I mean? The units, you know, define what it is. So we have radians, hell yeah, and then we have time. And then obviously it's the change in angle, change in time. Because just defining something as an angle, you know what I mean, that's a fixed thing, and then, you know what I mean, so it's the change in that angle, change in time. Okay. Yeah, it's you can, you know what I mean, if you have 1 second, you can define that angle. You know, that's why if it's radians per second, you're already saying like, hey, it's already the seconds has a unit 1 to it. So this is, you know, in 1 second, this is the angle that we're moving. And I'm just going to call it phi for the video. Everything's phi. Okay, so yeah, so for this component, then and this goes to just, you know, phi dot. You know, that is basically the same thing as r dot. R dot is a oh. And then this is interesting. Yeah, because it's so the change in the vector is this. It's the whole product of the whole shebang. Because we're saying the vector r is some sort of scalar component of the radius, but it's in the direction of the radius. You know what I mean? Wherever the direction of the radius, the radial direction. That's the direction you're going to move this many units to get to that position. So this is a position vector, and this becomes a scalar. So then when we take, this is a scalar and this is a vector. So we have a scalar r vector in the like a unit vector in the direction of the radius. Got it? And then when we do the derivative, first times the derivative of the second, first times ER. So we have this vector, we're taking the derivative of the vector, and then plus the second ER times the derivative of the first, so that's R dot. And then rearranging, and they put this one first, so we have R dot, change in position in the radial direction. We already said that's just linear velocity, you know what I mean? So cool, that's velocity radial, and then plus this term, R, the unit vector in the radial direction, that vector, we're changing that vector. So if we go down here, so cool, so this is a change in that vector, and this was, so E dot R, the vector E dot R, the radial unit vector, the change in the radial unit vector, this dot means change per time, so we're going to have D, the radial unit vector, divided, dt. So we're going to have the derivative. So we're basically we want to observe. See if I can use some of my tactics. Observe the change in the vector. Yep. Oh man. Is there a dot on top of that? No, it's just not a dot. Yeah. So the dot is. So we're taking that. Yeah. So, yep. We're taking this. The unit vector in the radial direction, and we're taking the change in that. We want to find the change in that vector with respect to time. That's fascinating. And I guess, going back to, if this is the direction I'm pointing, how could I have a change in that direction? You know, if the unit vector says, hey, I'm going to be pointing this way, a change in this direction has to come from some other direction. You know what I mean? And so, that has to be the case. So I think that helps me, even though it probably doesn't help anyone. All right, I had to take a little break, man. So what were we trying to do? So we're trying to take the derivative of this, and so it's the change in the unit vector, change in time, and then I had to look up what the hell it is. It's called chain rule. You know what I mean? And I get it, you know what I mean? I get it from the perspective of like, well, what the hell is the change in the radius? Change in the, like, what is that? Like, maybe you don't know, you know what I mean? I think it's synonymous. Let's take maybe a side, because man, let's maybe talk about stuff that I might know. And this is good because we are doing differentiation. With we're taking position, differentiating to get velocity, differentiating to get acceleration, and it might be easier to go the other way, where we have and this might not lead anywhere, but acceleration of gravity 9.8, cool, and by definition, this is classically, great, you have that, but then throw some units at this, you know what I mean? If you just do that, it's like totally naked. So we got to do acceleration is even just this, change in velocity, change in time. And then even do the units on acceleration. Acceleration is 9.8 meters per second squared. That's usually how people write it. And it's not useful to write it that way. It's very useful for your intuitive development to do 9.8 meters per second. And then I just do this second. That gets you halfway closer, but it just really changing it up. 9.8 meters per second. You know what I mean? Or even just putting acceleration 9.8 meters per second per one, even just writing out second, you know what I mean? Hell yeah, there you go. So so when something like this comes up, you're just like, well, I don't know. And then definitionally, going back to the and I would write this, I just don't want to write a lot, but acceleration is, change in velocity divided by change in time. Cool. And then you can do the next one. Acceleration is change in velocity, change in time. And then you can go dv dt. Cool. You know what I mean? Do those steps to be like, oh, okay. And I don't know if I will talk about how this is kind of an average. I mean, you're being like, well, let's say I know the velocity here, the velocity there, and I know it like took 2 seconds. You know what I mean? And so I just know this is, I dropped a rock off a cliff. You know what I mean? So and there's just 1 second. So well, I don't know. Oh, well, yeah, this is a constant, so obviously in 2 seconds, the velocity would be double. So I'd have like, oh man, struggling. 20 minus 0.4 though, it's 19.6. So I would have velocity here, 0, 19.6 meters per second there, and it took 2 seconds. So if those are the two things I know, hell yeah, you put them into there. So your change in velocity is 19.6, change in time is 2 seconds, and then you get that 9.8. Hell yeah. I mean, isn't this by definition saying like, whoa, like this is the derivative of velocity with respect to time, where if we take the time just down to just a tiny interval. So let's do one. You know what I mean? Holy Toledo. So let's say, like, what would be my change? Let's say a hundredth of a second, 0.01 seconds. If that was my set, what would be my change in velocity? Well, you take 0.01 times your acceleration, and we'll talk about that just in a second. And I get a change in velocity of 0.098. So we're going to say here I'm 0, and right here I'm 0.098. And it took a change in time of 0.01 seconds. So even there, we made our dt real small, you know what I mean? And we found our velocity changed by 0.09 divided by 0.01, and we get 9.8. And so because this is a constant, we take our velocity anywhere, and then very tiny time later find our change in velocity, and then we would still get that. Okay, so that means for up here, we can just say A is equal to dv dt. So we can just throw that in. So we just go dv dt is equal to 9.8. And even right here, this is such a great opportunity to give this something extra. You know what I mean? Let's say it's a variable t to the 0, and it just changes your life. You know what I mean? Just like that, you're like, whoa, I didn't know it had a variable of time in it. Well, yeah, it's time to the 0. So this is saying at time is equal to 2 seconds. What's my acceleration? And then let's get it back to this. Acceleration is 9.8 t to the 0. At 2 seconds, I'm going to go 2 to the 0 power times 9.8. Well, any number to the 0 power is just 1. So we got 9.8 times 1. And then we just have a constant acceleration. But this form right here will change your life, because you're just like, oh, I didn't see that. I didn't see that acceleration is the change in velocity, change in time. And isn't technically this acceleration a vector? You know what I mean? Where you'd have that as a vector. That might help me in doing some better analysis. But now, the classic is just we'll separate variables, and now because I want to maybe find the equation for velocity, so we'll go dv is equal to 9.8 t to the 0 dt, and I'm going to get rid of the vector sign. I don't even know if it exists. Anyway, so now we got dv is equal to 9.8 t to the 0 dt. We're going to integrate both sides. This just becomes v. And this becomes 9.8. Let's do the integration correct. We're going to go t to the 0 plus 1 divided by 0 plus 1. You know what I mean? That's the classic form of integration. and then we're going to plus a constant. So this comes out as 9.8 t to the 1. Hey, let's still keep that power, and divided by 1, so it's just 9.8, plus a constant. And now we got to figure out what the hell we're dealing with. Because if we're dropping a rock like off a cliff, well, at time is equal to 0, our velocity is 0. Cool. So we're going to throw in 9.8, 0 to the 1 plus c, and our velocity is 0 on this side. You know what I mean? And then we can see that 0 is equal to 0 plus c, so our constant of integration is 0. So now we have a full equation for velocity. Is 9.8 t to the 1. That's it. Cool. Equation for velocity. Now we'll do this a little bit faster for position. We know that the definition of velocity, change in position, change in time, we can do all that same cool stuff. Velocity is dx dt. So cool. It is dx dt. Excellent. So now we can go 9.8 t to the 1. And yeah, well, let's try one though. You know what I mean? So here, if this is equation for our velocity, we're going to say, oh no, I don't know if this is going to help us. Anyway, well, let's keep plugging. Do the same thing. Separate variables. We got dx is equal to 9.8 t to the 1 dt. And now we're going to integrate both sides. So we have an equation for our position. This is 9.8 t to the 1 plus 1 divided by 1 plus 1 plus a constant. So we did our integration. This comes out to, this will be 2. So it's 9.8 divided by 2, 4.9. T to the 1 plus 1 is t to the 2. And, we'll just do it real fast. If we throw in at time 0, what's our position? We're just going to say our position is 0 up here. You could change it. You could say position is 0 down here, and that's totally fine. You'll get a different value for c. But if we say at time 0, our position 0, c 0. So now we have an equation for position, 4.9 t squared. So what we're going for, if you're just like, why the hell am I just going over that, is we're trying to get back to why the chain rule works. All right, sweet. So yeah, I just really want an example right here of why, like, hey, if I have a derivative e to the t, well, why don't I just differentiate with respect to time? And there's a lot of problems where you don't want that. You want because right here you're going to have the derivative with respect to the angle, and then we're going to have the angle, the change in the angle with respect to time. And we already kind of know this as a quantity that we use a lot, and it's radians per second. So that is angular velocity. So that's why we do the chain rule there. And I think it boils down just because, like, it's yeah, I mean, well, let's try it. Yeah, let's see if I was going anywhere with this. So we have an equation for our velocity is 9.8 t, and equation for our position is 4.9 t squared. And you know what I mean? We could get oh, this is where I was going with it. Yeah, you see this a lot. Acceleration is change in velocity, change in time. But that's the thing. There's so many problems where you like the time component. I don't know how to say it, but the time component messes it up. Like, it doesn't mess it up in Excel. This is great. There's so many physics problems that I can just throw in Excel, and then, in a column go 0, 0.01, 0.02, and this is going to be seconds. And then calculate the acceleration, calculate the velocities, the change in velocities, and then figure out where the hell everything's going. But yeah, sometimes this isn't useful, so you can go dv. You can always do the chain rule. You can take the derivative with respect to literally anything. And so we're going to take the derivative with respect to position, dv dx, and then we're going to go dx dt. You know what I mean? So now you can see that these would just cancel, and we would just get back to derivative of velocity, derivative of the time. So this is totally saying the derivative of velocity, derivative of the time is the same thing as the derivative of velocity, derivative of x, times derivative of x dt. And how do you say that? You say derivative of x with respect to time. You know, it's not derivative of x, derivative of t. I don't think you say it that way. But in general, it's dx. It's the same. It's like, hey, all you're doing is changing your x and changing your time. And getting a quantity for that. You know what I mean? So I'm going to take my... so if I'm driving in a car and I'm here to here, and then the next point I'm here to there, well, and the change in time was the same. So I'm going to say, hey, same dt on both those, but my position got a little bit bigger. This number was smaller. So if I just take this ratio, smaller number compared to, and this is just going to be a normal number. So now I have, hey, at this point, I have this number divided by this number. Cool, we got a number. And then at this point, well, I got a bigger number divided by that same number. So now I can see this value is bigger. So evaluating right there, my change in position, change in time, hey, it was okay. But evaluating right here, hell yeah, it's bigger. So what the hell is position divided by time? That's, definition of velocity. We got meters per second. If this meters per second is bigger, got a bigger velocity. Okay, so, but now, what the hell is changing position, change in time? Well, it's the same thing. It just gets a lot more heady. You're like, well, let's say, oh, and it's you have to change your position and then figure out what your change in velocity is. You know what I mean? So if we do the whole dropping off a cliff, what are the positions that we know? Well, I know in 1 second, and we can talk through this because this is very useful just to do the basics. In 1 second, I'm going to have velocity 0 here. And 1 second later, I'm going to have a velocity of 9.8. So cool. This is the first one to be like, well, how far did I get down this distance? You know what I mean? This is kind of the first head scratcher that you should do 1,000,000 times to get used to, because this pops up so much that you're just like, well, just like anything, if this is the town I live in, and then I want to get to this next town, and I hit the interstate with a constant speed, 60 miles per hour, and I drove for 1 hour, and this was 60 miles away, or just, that was the deal, then, because we're saying here, we already have our time of 1 second, and here we had a time of 1 hour, and then we had a speed of 60 miles per hour. Constant speed, we went 60. But here, we're starting at 0 and then ramping up consistently to 9.8, linearly, you know what I mean? Acceleration is linear with respect to time. For every 1 second, you're just increasing your speed by 9.8 meters per second. That's the definition of acceleration, or the definition of constant acceleration. Okay, so to get from there to there, you would have to use your average velocity. And it's just a good equation to know. It's just 0 plus 9.8 divided by 2. Doesn't matter what these are. You could have a initial velocity of 10 and then a final velocity of 20. Your velocity average, split the difference. Visually you see that as 15, or you can see it as 10 plus 20 divided by 2. Alright, so even right here, so we're gonna have a velocity average of 4.9, and it's gonna be 4.9 meters per second. And this is another, let's say you just do have velocity. This is great for factor label stuff, like all the time, where you're like, especially just in a crunch, you're like, I have this value of 4.9 meters per second. I know that I want meters, so now, okay, and then, so meters is upstairs. You can just visually see, and obviously we want a number of, we don't want meters to the -1. We want meters upstairs. We don't want 1 divided by meter. So So now if I need to get rid of this time aspect, or sometimes it's even easier than that. You just like, well, 4.1, and I also have 1 second. And I just don't know whether to multiply or divide. We'll figure out what you want, and then figure out the thing that has it. You know what I mean? But if this is some term that's like, kilograms per meter. Let's say water, 1,000 kilograms per meter cubed. And for whatever reason, I want to know how many meters cubed is in an Nalgene, which is, you know what I mean, about 2 pounds, 32 ounces, 2 pounds. So that's 1 kilogram. Cool. So I have 1 kilogram, and I want to know meters cubed. I kind of do this like, hey, that's what I want, but it's downstairs. You know what I mean? So obviously, I don't multiply this by nothing. You know what I mean? The meters cubed would still be downstairs. So then I know that I need to divide this by something. And 1 kilogram. You know what I mean? That's the first place to go. And then, hell yeah, most all the times your other things will cancel. And then so 1,000ths. So 1,000ths of a meter. Who knew? A Nalgene was 1,000ths of a meter, cubic meter. Okay, so there you go. So obviously 4.9 meters per second times time of 1 second. We're going to get 4.9 meters. All right, so sweet. So we got 4.9 meters right there. And what the hell we were trying to find? Chain rule. We wanted to figure out what the hell dv dx meant. So when we changed our position, we changed our position from 0 to 4.9. So we'll just call it 4.9. So we changed our x by 4.9. How did our velocity change? Our velocity went from 0 to 9.8. So our velocity went from 0 to 9.8, so our velocity went from 9.8. And we get a dv dx of 9.8 divided by 4.9. And we get a dv dx of 2. You know what I mean? And I think we should carry this one farther, because now at 2 seconds, our velocity is 19.6. Our average velocity is 19.6 plus 9.8 divided by 2. So we got a velocity average of 14.7. So now we're going to go from 4.9. All right, hell yeah. So we're going to go from 4.9 meters. And in 1 second, our velocity is 14.7 meters per second. We're going to go for 1 second. We're going to go another 14.7. So 4.9 plus 14.7. We're going to go 19.6. But, now you can maybe get there faster. Wait, our velocity changed by 9.8. We already know that. But hell, that time our position changed by 14.7. So 9.8 divided by 14.7. So now our change in velocity divided by our change in x is 0.66. And so that's wild. And that number is just going to get bigger. Change in velocity is always going to be the same. Change in x is going to get hella. Until under ideal circumstances, obviously you're going to hit terminal velocity. And but just for the ideal sense. So now this equation will definitely changes. So even just right off the bat, we know that this isn't a constant. Just like for acceleration, that was dv dt, and that was a constant, 9.8 t to the 0. It was just a constant equation. So how do we actually find that? Maybe I don't even know. No, we're good. Let's just grab some more paper. So at this point, we have acceleration, dv dt. We did the chain rule. We got dv dx. Kind of figure what the hell that is, and dx dt. And the cool thing about this side is we already know dx dt. Dx dt is just the definition of velocity. You know what I mean? It's change in position, change in time. It's a change in position, change in time. Like, that definitionally as velocity. So we can just do this. dv dx times velocity. That's acceleration. All right. And I guess that's equal to 9.8. But is this 9.8 still have a t to the 0? You know what I mean? Like I feel like that's where like I'm unsure if you can get rid of that or something. And actually, I might not have any more. You know what I mean? Actually, because well. Yeah, I don't. I mean, I have this. If you wanted to figure this out, you'd have to separate variables. So you'd have to go dVV is equal to 9.8. Oh, I got it now. This is also t to the 0. This is also x to the 0. Is that right? No, I don't think so. Yeah, acceleration is 9.8 at input any t value, input any time, and you'll get 9.8 acceleration. Now, acceleration is it is. So that's so fascinating how that's hard for me to see. How it's like, okay, so if I have this thing falling off a cliff and it goes from position 0 to 4 to 17 to like way the hell down here and kaput. So we got 4.9. Well, this is a change in 14.7. You know what I mean? So now we got 14.7 plus 4.9. And we got 19.6. All right, and then hella. You know what I mean? But at what position, you know what I mean? Give me any position. Be like, hey, at 4.9, what's my acceleration? You know what I mean? You know, it's a Jeopardy question. 19.6, what's my acceleration? Well, obviously, acceleration doesn't change. So I think this is such a that's why I went exactly to this. Because this is the most useful thing in physics. And it's weird that I say, like, yeah, the first chapter of physics is just taught wrong. But, I mean, it's because they don't just jump into the calculus. I mean, you should just be jumping right into... But I don't know. That would probably confuse. Because even now I'm having a hard time even figuring out... But that's the thing. What I'm doing is figuring out a chain rule, a demonstration of the chain rule that I could probably understand. Besides just like, just using the chain rule and be like, well, I really don't know exactly what's going on with the numbers, but I know it's a useful thing. That's what I'm trying to get better about. But yes, this is 9.8 x to the 0. Give me any position, and guess what? My acceleration is still 9.8. Okay, so now we don't have to use the t term. We brought that upstairs. So now we have x to the 0 dt. So let's clean this up. So we, yeah, and it's fun just to keep doing it again. So dv dt, chain rule, dv dx. Now we kind of understand what the hell that is. And now we know that this side is dv dx times velocity. That's velocity. And what else? Cool, and we kind of got it. So now, and let's not throw the number on. Sometimes it kind of, well, yeah, maybe both ways. So this is going to be a dv dx v. We need to separate variables, so we're going to go a dx is equal to v dv, and then we would integrate. But obviously, it's going to make more sense if this is a constant. So we're going to do that same thing we did with time. So we got 9.8. Oh, that's how we did it. We had this on that side. So we're going to go dv dx of v is equal to 9.8. Get some more light. Alright, heck yeah. And this is going to be x to the 0. Okay, now we can separate variables. So, and then I'm going to bring this v over here and that up there. That's all I did. So I'm just going to go v dv. because that looks like we can integrate it, is equal to 9.8 x to the 0 dx. And I have to admit, you know what I mean? I get from here, it's hand waving for me. You know what I mean? It's like, great, we do an integral and it makes sense. But now, this is v to the 1. You know, anytime you do your integral, it's like, hey, red flags go off. You know what I mean? Asterisk, asterisk, asterisk. Make sure anything, it's very useful to get your exponent, even if it's a 0. That indicates, yeah, okay, let's do it. So we have, so this is going to be v to the 1 plus 1 divided by 1 plus 1 is equal to 9.8 x to the 0 plus 1 divided by 0 plus 1. I mean, because this week I made a video of just like, yeah, let's integrate x, and I just said that was x squared. The integral of x was x squared, and then I just left it like that, and it looks 100% right. For what I just did it again, and I'm just like, that looks 100% right. Integral of x to the 1 dx is x to the 1 plus 1 divided by 1 plus 1 plus c. So that's x squared, 1/2 x squared. It's like, holy Toledo. You know what I mean? So, all right. So now we have this x to the 1. This is 2, so we have 1/2 v squared. And then this is 9.8 x. And there you go. So we did it. And what the hell were we trying to do? Well, I mean, at the end of the day, yeah, just get an equation with respect to x. And I think if we go back to our circle, it's like, hey, we want an equation for velocity where we can just pump in phi and radius. You know, those two things, radius and phi, and we can do it. But, I mean, the bummer is that this other term gets in here of radians. The definition of radians, what do we say? Well, let's do the axiom backwards. So, radians times radius is something normal. That something normal in this case is going to be arc length, you know, s. And so what this will say is radians, that symbol, times the radius is arc length. You know what I mean? And for this video, we're going to use phi. I just like to use theta. You know what I mean? I think that's typically what people use. It just looks better. Or I guess if you just use something 1,000 times, it's just bizarre to use something else. Alright, so, alright, hell yeah. So now I'm feeling a lot better about myself and just being like, okay, I get it. Yeah, we want an equation for velocity, you know what I mean, in terms of these two variables, and then we wanted to relate it to what the hell radians was. So we got radians per second times radius is also something normal. That something normal in this case is velocity. I get that arc length doesn't really, you know what I mean, jive as something normal, but that it's like most people, like I didn't know that after graduate. I didn't even know that in college, that radians meant, you know, or radians times radius was arc length. You know what I mean? That's probably why I failed, like, what was it? I guess just surveying class, you know what I mean, where you try to do equations of like roads and stuff and circles. It's just like, why the hell is a circle so complicated? Well, yeah, you just don't even know that friggin' angle, you know what I mean, in radians times your radius is that distance. I mean, that's the change your life. I wish professors would have been like, no, you probably don't know this, and now you do. Okay, so but yeah, same thing with radians per second. So radians per second times radius is velocity. So now we could just say that, well, how did I want to get my, you know, in terms of, well, kind of, yeah, just, you know how they did like r hat is actually just velocity in the radial direction? No, not necessarily. Sorry about that. Because, let's go back. As a vector, r hat is two things. It's a scalar. Is that right? Oh, I wish I had. No. Yeah. R hat is the two. Yeah, obviously, yes, the velocity thing that we're trying to get. Yes, it's this. See if mentally I can just do it. Is the scalar No. It is it's the change in the radius, which is a scalar. It's a scalar quantity. It's the scalar change in radius, which is just dr dt, plus then we have yeah, I don't want to look up there. I'm trying to do it 100%. So we have the yes, this is the change in the radius vector, and the radius vector is scalar unit vector in the radial direction. So it's going to be first times the derivative of the second plus the second, plus the second times the derivative of the first. So this is velocity radial velocity. Got it? And then this is tangential velocity. It's just a little bit more confusing because this term is a chain rule. It's okay. Got it. Because let's see. This component is this. So this is your change in angle, change in time. That's radians. But this, I think that's where I just kind of get the unit vector in the tangential direction is the change in the radial radial unit vector with respect to that angle. And I guess now that makes more sense because I don't know how to put words to it that just saying the change in because this would be the change in the radial vector with respect to time. I think we just kind of proved that sometimes that's not useful. It's like, cool, I don't have Excel. I can't throw a time in for all these and figure out what the acceleration is. Like I have a problem that says, hey, at this position, x is equal to 0 and then x is equal to 20. At 20, I want to know the velocity. That's it. You know what I mean? So you'll get tons of problems in physics that are just like, yes, at this position, I want to know the velocity. Okay, thank goodness. Okay, so now this makes sense because I'll take and especially that Schwalm's book. This is where I kind of gain that knowledge of just like, hell yeah, the calculus and it's more the differentiation because you have to understand that acceleration is change in velocity, change in time, and that is a differential. And then then you separate variables. So everything's all about just the fact that F equals ma, and we can talk about this just a little bit, is, you're trying to find the forces on things. So like one of the problems is like, hey, drop a steel ball in the ocean. And guess what? There's a force in this direction. This force is proportional to the velocity. And you're like, oh, well, that's nice. And how easy. You know what I mean? It seems like going to be like an easy problem. But no, because you do have the weight. Weight is mg. But then you do have motion. You know what I mean? Hey, its velocity is 0 here. And then at some point, it's not 0. So you know you have acceleration. You know what I mean? So that's the whole thing about F equals ma. Like, hey, when we do this experiment, we see a velocity go from 0. So sorry, this side. When we look at acceleration, eyeballs on acceleration, eyeballs on the mass, we see it go from 0 to some velocity. Must have acceleration. And then we go here. Because we're in the observable universe and we know that we have an Earth underneath us, we at least have one force. You know, we have mg. So cool. Typically in free fall, that's all we need. Because if that's the only force on this thing, we're going to go acceleration of 9.8. I think we've done that. And then you definitely want to use Kepler in taking no shortcuts. Force of gravity is g m1 m2 divided by r squared. You know what I mean? And this m2 r squared, This is the mass of the Earth, radius of the Earth, gravitational constant. All that crap is just 9.8. Who knew? You know what I mean? And but you should always go back to that. Anyway, so in this problem, you do have a force. You have a drag force up, and so you're gonna get that mg down. So you have a force down. So this side, we're calculating. So the forces on this side, we're going to sum them all up. Mg down, and then we have an upward force. K velocity. That's going to equal mass times acceleration. Well, and we just want to know, well, the acceleration. And we know it's not just going to be a 9.8. You know what I mean? To find it in this equation, let's talk about it. How the hell did we find it in this equation? We said g m1 m2 over r squared was equal to that same mass times the acceleration. So we didn't have to do a damn thing. We just crossed out m's and then got a constant. Where here, if we wanted to find the acceleration, we would have to divide by mass, and then we would have an acceleration is mass gravity plus k times the velocity divided by m. But guess what? The second you drop this in the water, you don't know its velocity. You don't have some sort of accelerometer on it, or any sort of equipment. But you still want to know the velocity, and because it's a problem in a book, they're just like, well, what the hell is that? So let's do this one, because it'll really help us figure out. We'll finally finish the chain rule. We'll definitely come back to that, but we definitely have to take this side tangent just to take a problem that potentially seems easy, or for most people, be like, nah, probably none of these are easy. But so we got mg, so we have negative mg. Sorry, that's negative. So downward force mg plus kv is equal to that same mass times acceleration. So we say this is mass times dv dt. Cool, but right now, what the hell good does that do? You know what I mean? There's nothing over here that's a function of time. We have something that's a function of velocity, sure. Well, I'm thinking, well, maybe you could, but yes, you could. That was the thing. It's just like, well, couldn't you get a because you have velocity here. And well, let's simplify this. Mg plus kv is equal to m dv dt. And so if we wanted to, and how the hell we... Heck yeah. Now I'm wondering like where the places you run into issues are. Because here... well, no, we do it. So you just take the time upstairs and then all this crap downstairs. So we're just going to go dt is equal to m dv, all divided by negative mg plus kv. If we do that, sure, we can differentiate both sides. And then we'll get an equation of time is equal to, velocity. You know what I mean? Because this is a dv and we have a v. We have everything else is constant in here. And because v is downstairs, I mean, basically all this is saying that this boils down to dv divided by v. That's v to the 1. So obviously we got, if we integrate, we're going to get, this is v to the negative 1. So so we're going to have v to the negative 1 dv. When we integrate, we're going to go v negative 1 plus 1 divided by negative 1 plus 1 plus c. So cool, we get v to the 0. Looks happy, but now we get divided by 0, and this becomes just the natural log. So essentially we'll get an equation that says time is the natural log of velocity. And then if we did it in reverse, we'd get velocity is e to the t or something. I think that's how it works. Don't quote me on that. But there you go. So that is pretty much right. So you'd get an equation for velocity as a function of time, and so yeah, you could do that. You know what I mean? That's what you could do. And it's not an equation for position though. You know what I mean? And your velocity is going to be hella changing, and so even for this, you still don't know how to get position. You would still have to throw this in Excel and say for every time, 1 second, 2, 3, 4, 5, 6, and then you would find your velocity. Hell, at least you had an easy way to find your velocity equation. So you would have one. Well, actually, it starts out. Oh, that's weird. How like that whole thing about dropping something in the ocean. I guess it actually has to go. It has to start from 0, go to some max, and then stay. That's what it does. It starts from 0, definitely goes faster, but then it hits some max. You know what I mean? It doesn't go up and then down, but it just hits some max, and then it'll actually, which is cool because then you get an equation. It's like an equation for height would be like, well, like babies are like so tall, and then adults are that tall. So you would have an equation for height. I did this once and I actually forgot, because I tried to dial it in. I was just like, can I just get an equation that starts, like right here, and then pretty much goes up and then just totally tapers off. Those are going to be your e to the t's. Those are going to be your natural logs because it'll never get above a value ever. And so those are useful equations for like, well, no one's height, even if they got to 1,000 years old or 115, is going to keep going up. It's going to plateau right around that. I don't know, maybe just even 30-year mark. Okay, so this one would be like 1. And then you're going to get 1, 2, let's see, 2.9, 3.7, and then 4. Am I doing it the wrong direction? You're gonna be, you're gonna 3.7, and then well, let's just say 4.1, and then 4.3, and then 4.4. So here's a change in 1, change in 0.1. This is a change in 0.2. This is a change in 0.4. This is a change in like 0.8. This is a change in 0.9, and this is a change in 1. So there you go. So you have so that's basically what that would be. And so if I wanted to get an equation for position, I would just be like, well, I'm just going to say and then at 0 we have a velocity of 0. I'm just going to say that if I wanted to get an equation for position at second 1, I'm going to say, well, my velocity was 0, and then it was 1 meter per second at position 1. And again, it's that same game. It's just like, well, were you driving 1 meter per second the entire time? No, I was 0 and then slowly ramped up. Cool. So my average speed here is 0.5 meters per second. My change in time for this scenario was 1 second. Now in Excel, you can make this super tiny. Your change in velocity is going to be super tiny, but you're going to take that tiny number, divide it also by a tiny change in time, and you're going to get basically, you're going to get meters. You're going to get meters per second times time would be meters. So there you go. Time would cancel. You get meters. All right. So for this, we would have a position of 0.5. At 1 second, we'd have a position at 0.5, and then we got velocity 1 to 2, average velocity of 1.5. So we must have gone another 1.5. So now we went 2. You know what I mean? 1.5 plus 0.5. So that's what we set up in Excel. The difference between here times my change in time plus the last position. This is going to be 2.45. So it's going to be another 2.45. So we're going to go 4.45. That's position 3. Then we're going to go, there's 0.8 between here, so we're just going to go 2.9 plus 0.4. That's going to be 3.3 is our average velocity. So we're going to go another 3.3. So it's going to be 7. So the 3 plus 4 goes to 7. 3.3, 7.75. And I think I'm done, but hell yeah. So now I basically have an equation for position. But how the hell would we do that with the chain rule right off the bat? Again, we have this thing going in. We have a weight, mg, going down. We have a force due to drag of some sort of constant times its velocity. Now, if the velocity is 0, well, this is 0. See how that works out? But if this velocity is its max, so at some point, this drag will be bigger than that. So at the point that this drag equals this, then this thing will be a constant velocity. All right. So we have the force. We have the force down, negative mg, drag force up, kv, equal to, so this is F equals ma. You know what I mean? These are the forces in the known universe that we're familiar with, that we can identify. This is the mass that we're observing, and we want to figure out its acceleration. We know that acceleration is dv dt. So now we can go negative mg plus kv is equal to m dv dt. But we don't want dv dt, so I'm just going to say this is m dv d position dx dt. Hell yeah, I definitely want position. And guess what this is? You know what I mean? It's exactly the same as another variable we already have in the equation. So now this becomes v. So now we got negative mg plus kv is equal to m dv dx v. And now we can, the only thing that you don't want to make mistakes on is this position. There's nothing else. This is a constant. This is v, v, v. Everything else is constant. Nothing, and I guess same rules apply. I guess everything else is x to the 0. You know what I mean? When you have a position of whatever, what is this constant? You know what I mean? So yeah, you just bring the dx over here. Everything else, and I'm just going to do this as v dv divided by negative mg plus kv. So now this is it's still a natural log thing. It ain't easy peasy, but then when you integrate, you will still get you'll get an equation for position. Position is some sort of alright, hell yeah. So my camera overheated, but we're gonna do another round of this. So let's see. So from that example, we were able to use the chain rule to come up with an equation for position as a function of velocity. Is that what we did? Oh well. We have in this example. Now you have an equation that has position on this side, velocity on that side. But what you might want to know is the velocity at every depth. So then you would take this. Whatever this is surrounded by, bring it all over there, and essentially get something with I want to know the velocity, and then I want to input x, and then what other garbage is around it. Okay, so that was I think I'm pretty satisfied with the chain rule on that and understanding it. So let's go back to this example and see if we can figure out anything more about it. And at the end of the day, hell yeah, all this is saying is that we have a velocity component tangential and then in the radial direction. So, if here's our point, we can either go that way with velocity or we can go that way with velocity. Yeah. But yeah, let's. That was the whole point, was to see if we could use the chain rule. So we got our position vector. It's the scalar component with a unit vector in the direction of the radius. Got that. And now we're going to differentiate that. So that's going to be d dt. So whatever the the position of the radius, the radial vector. Anyway, so then it's just the dot product. So we got first times the derivative of the second plus the second times the derivative of the first. Okay, and again, this is just velocity, radial. So this is just like, hey, the radial velocity, got that. But this term is the one that we were, you know what I mean? And I don't know, just keeping on doing it might not help, but we have this term is d. This is the unit vector in the radial direction. And we want to know how it changes with time. And again, so we have that person walking along on a path. This is the radial direction, but at some point, like, hey, they might want to deviate from the path. And the only way to do that is to move tangentially. And so we just know that as the tangential direction, you know, which we'll call the, you know, and here's our radius. Okay, so but they do use the chain rule on this, and they do d, the unit vector in the radial direction with respect to the angle, times the change in the angle with respect to time. And then this is the definition of radians per second. So this is angular velocity. This term just turns out to be the unit vector tangential, the tangential unit vector. And I guess, I mean, that's the part I just have to throw my hands up in the air. You know what I mean? And it seemed to make sense just from the fact that, hey, if I'm out here and here's my radius, like how can my velocity change? Because if I'm stationary, I'm stationary. I have no velocity. But yeah, I could go around this loop, or I could go this direction. I mean, just like visually, that makes sense. I just have a hard time right at this step. I don't know fundamentally what this actually this lower term, you know what I mean? But I guess we're saying that, hey, let's take a little slice. So we got d, we got that angle change, and then we have this, and so yep. Yeah, I think I'm just going to move on at that point. Because, and that's a bummer, because I thought just kind of explaining to myself might have helped. I'm going to grab this sheet of paper just in a sec. Okay, so, but here's the, excuse me, here's the full setup, where you go from position to velocity, and then you got to go from velocity to acceleration. So you got to, and this is a product of three things, you know what I mean? You have three terms here, and then so this one's going to be the first times the derivative of the second. And these are vectors. So, and then it's going to be plus the second times the derivative of first. So we have, so this is velocity, now we have acceleration. So this is just saying, hey, radial acceleration. And that makes sense. If we have our circle and we're accelerating this direction, well, we're going to, yeah, that's just linear acceleration. But that's what that term is. This term, this term was linear velocity. But now this is going to be one of those other things that's just kind of difficult, you know what I mean? So then we go down to, you know what I mean? We go over to here, and this is the same thing. It's we do the chain rule, and we get an omega, and then we this, the change in the radial direction with respect to theta is just this. It's the unit vector. It's the tangential unit vector. Hopefully I'm saying that right. Okay, so we did those two terms. Now for this next part, you have to do 3. You have to do like, you know what I mean, the first 2 times the derivative of the second. Plus, you know, maybe the first and last times the derivative of the, I'm sorry, the first 2 times the derivative of the third, and then the first and last times the derivative of the second. What's the derivative of this with respect to time? Well, that's the omega, and this is the same game you play with acceleration, is dv dt. What's v? That's dx dt. Same game you play with radians per second. So this is change in angle, change in time. So then we would have d theta dt, and then we would have to take the derivative of that with respect to time. And then we get the second derivative. And I think you write it like this. The second derivative of theta. And then this time component, though, is squared. So there you go. But yeah, for whatever reason, even just this, writing it correctly, probably is significant and means something very particular. Or yeah, it's like you definitely just square the time component down below, or I mean that kind of comes out. Okay, so and that's just alpha acceleration. So the change in omega dt is angular acceleration. So we have the first angular acceleration and then the last. So there's that term. And then, yeah, and I guess we're doing it in the correct order. Now we're going to do, so we did the first and second, change the, oh, no, we did it kind of in reversed order. There's that one. And now we're going to take the second and third times the derivative of the first. So we're going to go plus r hat omega. Alright, so we're going to go r dot, which is velocity, omega in the direction tangential. Okay, so those are the 5 terms. And, you know what I mean? This one's just acceleration, you know, just obviously that's just acceleration. And, I mean, so you could write this as, but yeah, that's acceleration. This is velocity in that radial direction. And then these are your tangential directions. Just a second. Same thing happens, you know what I mean? You have this term, which, the change in the radial direction becomes the unit vector in the tangential direction, plus an omega. This becomes kind of the same thing. The change in the tangential direction becomes the radial direction times an omega. And this also brings about a negative term. And I think this is a typo in here where this should be negative. You know, usually texts don't make typos, but holy Toledo, because then when you come down to here, obviously you're grouping terms, and that is a negative term. And this is the normal acceleration, you know, back to this is why, you know, if something's spinning around a point on a string, it wants to go that way, but it's not. It's actually hooked into the circle, you know, by continuity of the string, and it has to accelerate back towards the radius. Because like right here, it has zero velocity. It has zero radial velocity. All its velocity is tangential. But right here, and if that was the case, it would be right here. But we find it right here, so it must have had some sort of, how did it get there? It must have had some sort of velocity towards the radius. And then so velocity of the radius is here, velocity towards the radius is something. And then you play that game. Well, you know what I mean, find the velocity average, and then you can find well, or you just know it went from 0 to, oh no, yeah, you take oh shoot, yeah, we'll do this example. All right, so and then yeah, so that term comes out negative. And then you group terms, and then this is where I can actually add value to the video. And it seems like such a waste of time to just talk about stuff I don't know to get to this point. So this is just the acceleration, linear acceleration in the radial direction. If you had no omega, that would go away, that would go away. And then obviously if you didn't have any angular acceleration, like spinning, if you didn't have an omega, you wouldn't have a change in omega because you wouldn't even have an omega. So that terms go away. And then what you're just left with is just, acceleration, just linear acceleration. Car going down the road, going from a stop sign, and then going faster. Cool, so you got that. The other thing that kind of pops out of here is you might have a circle. You might are going around a circle, whether it's like an amusement park. Something's going around in a circle. Anything that goes around in a circle its radius won't have any velocity component in this direction. It won't have any acceleration component in this direction. So this component goes away. And then this component, this is the velocity of the radial velocity. Is that right? Yeah, it just looks funny. Yeah, this is the radial acceleration. Even though this is over here for acceleration in the radial direction. This is an acceleration term. So if you have if your radius is changing with respect to time. So right here, this is our fixed radius. Now, if at another time that radius is over here or over here, you know what I mean? That's a change in radius. And so if you have that, you'll have an acceleration by definition tangential. You know what I mean? But if we have a problem that doesn't have a radius that changes, that goes away, this goes away. And then you're just left with these two terms. And you might get something like, hey, a saw blade on your table saw gets up to 3,500 RPMs, and we want to learn something about it. Well, let's say that's the omega, and it's constant. It's a constant number. There is no change in what did I say? Radial. There is no change in radial acceleration. Well, what do you call omega? Radial velocity. I think that's what you call it. But anyway, but your table saw also, when it's off, it's not spinning, and then when it's on, it goes up to 3,500 RPMs. So it did have, you could, for that problem, you know what I mean, find the acceleration, because it might take a split second to do that. Then you'll have a change in your, angular velocity. So the angular velocity here is 3,500 rounds per minute. Angular velocity here is 0. And you can convert revolutions per minute, and let's do that. Revolutions per minute, convert that to radians per second. Well, one revolution, so I can go one revolution is 360 degrees, or I could have bypassed it. I could just say one revolution is 2 pi radians, you know what I mean? But I like to go to degrees, and I'm going to say 360 degrees is 2 pi radians. So yeah, obviously the 360 degrees was redundant, but now we have revolutions. Now we have radians per minute. I'm going to go 1 minute divided by 60 seconds. And then we'll do all that, and then you'll get revolutions. Sorry, you'll get radians per second. Okay, so if we have just a circle problem with no angular acceleration, it just comes down to, does it just come down to one term? Is that what we just showed? Well, yeah. I mean, it kind of comes down to 2. I mean, if you just have a circle, it comes down to 2. Because you could have turned the saw blade on, and it could have some angular acceleration. And for sure, we're working with something spinning in a circle, so we do have an omega. We do have angular velocity. Angular velocity, angular acceleration. All right, so the crazy thing is, though, these terms aren't obvious. No, is that right? Is that true? Probably not. Oh, no, I apologize. This term's obviously obvious. Yeah, if we're accelerating in the radial direction, that was just a car going down the road. It's a linear problem. We can definitely see that. It's this term. You know what I mean? It's like, why is there an acceleration towards the radius? You know, if we're just spinning around in a circle, why is there? And this answers it. If you have a string and a little, something on the string, and you spin it, that string has tension. Spin it faster, that spring has a bigger tension. And the reason it does is because this ball wants to just go that direction. If it didn't have a string, it would be here, but because it has a string, it's over here. And if it didn't have a string, it's just going in this tangential velocity. And right here, at any point, you could say that it has no velocity towards the radius. So that's going to be this one. Now this one says, hey, our radius, we got into an elevator on Earth, and then we're going to move up the elevator. Well, guess what? Our radius from the center of the Earth gets larger, and so we're going to have, at any given point, we're going to have a velocity, a radial velocity. Now if that elevator is stopped and then gets up to speed, hell yeah, we're going to have some radial acceleration. That would be a good example of radial acceleration. Once that elevator gets up to speed, though, then we're just going to have this, radial velocity. The radial acceleration is easy. It's just like, well, the elevator was stopped, and then 1 second later, it's going. All right, so yeah, the elevator was stopped. A second later, it's going max speed. You know what I mean? So your change in velocity is that, max speed divided by 1 second, and then you got your acceleration. Once it got that max speed, it's not changing, so then it's constant. But then you get this term. This term says if you have a constant velocity this way, and you have an omega, you're something spinning. Because that's obviously what we're doing. We're doing spinning problems. You know what I mean? If it wasn't spinning, it would just be a car going down the road problem, just linear. But we're saying, hey, we have some sort of spin, and then we have some sort of velocity. And that's going to cause, what's going to happen is that you're going to get sucked up against the back of it. If you're standing facing this way, your back's going to get sucked up against the back of the elevator, because it's as you're going up, it's like pushing you, and this relates to our golf ball problem. Now, if you are and this angular accelerate, or if you're accelerating in the elevator, hell yeah, you're just accelerating that direction. And if you are accelerating this direction, how do I put this? You will experience. You won't experience a. In the elevator, if you are accelerating, that's a change in velocity, which by definition means that you have some velocity, and if you have some velocity. This attributes however you're rotating, you'll get this acceleration tangentially. You know what I mean? But like, why isn't there another term here that says like you know what I mean, 2r dot dot omega squared, it's because that wouldn't be an acceleration. That would be like a jerk term. So you have position, you have velocity, you have acceleration. That's the change in velocity. But then you have change in acceleration. So this term would be a change in acceleration term. And so if I go from 0 to 60, heck yeah, you feel that. I'm accelerating. You know what I mean? There's a force on me. A constant force. F equals ma. I have acceleration, have a constant force. If I have a jerk, well, that's the next thing. If I have a change in acceleration, well, then I'm going to have a change in velocity. I mean, a change in force. So instead of feeling like one force, you know, pushing me back to the seat, I'm going to feel a change in that force. You're like, whoa, you know what I mean? And then and so that's a change in the force. I go from like, whoa, I feel that force, and then after that is snap. You know what I mean? And yep, the change in that force is changing. So anyway, okay. So the two that I go to are these mysterious ones. You know what I mean? Like, could I just derive these? And we will. So one is, this is the r omega squared, and I guess it's minus. And what we're going to say is, we're going to say an omega of 1 radian per second. So every second we're going to get to that kind of that 60-degree mark. That's going to be our omega, and we're going to spin that way. The radius, we're just going to say a radius of 1 meter. Okay? And this is radians per second. There you go. We know that radians per second times radius of 1 meter is something normal. So we have 1 radian per second times 1 meter. That's going to be velocity. So omega r is velocity. We got that going. And our velocity is going to be 1 meter per second. This is the tangential velocity, so it's that direction. And okay, so again, we you know, I said it before. If we're tangentially moving that direction, we at this point we don't have any velocity towards the center of the circle. We don't have any radial velocity. And if we do have tangential velocity, we would just be wanting to move in this line. But that's not what happens when we're stuck to a circle. We move to that point, and that point is closer. You know what I mean? We moved over here. So just like our analogy of like just walking along a path, you know what I mean? And then you take a step, you know, that direction. Well, you had to move tangentially that direction. And like right here was my velocity. What's my velocity that direction? It's 0. And then right here, this is a bad example. Notice, like let's say we're here, but then we start to take a step that direction. Cool. So we've always had velocity this way, but now we take a step that direction. Our velocity right here is still zero that direction. But then we can say if this happened a time of 1 second, and then we covered this distance, let's say 1 meter, we really took a huge step sideways, then we must from here to there, we must have had so just like right off the bat, you know, don't make this mistake. It might look like my velocity right there is 1 meter per second. It's not. The thing to do is just double it. Velocity is 2 meters per second. And how can we prove that? You know what I mean? Well, let's, so this is our distance, 1 meter. And we were able to see that we got a distance of 1 meter in 1 second. What that gives us is our velocity average. Velocity average says we went 1 meter and it took 1 second. Our velocity. So cool. So now you have basically this little thing, and you have velocity here is 0, velocity here had to be a max, and then your velocity average was 1 meter per second. So what's the definition of velocity average? You know what I mean? It's the first times the last. You know what I mean? It's 0 plus v max and then divide by 2. You know what I mean? But if we started with 0, then our velocity average is just v max divided by 2. Well, we know our velocity average, and then so we can bring this 2 upstairs, and then so our v max is velocity average times 2. And so that's going to be that 2 meters per second. Okay, so that's what happens. And if that's the case, I mean, well, we knew we had no velocity here. We had to get there. We're just assuming we had velocity. At the end of the day, that is the definition of acceleration. Alarm bells should go off and be like, hell, we are accelerating that direction. So, even right here, let's say I'm still moving at a constant velocity this way, but I did move that way. So I would say this has a let's see. Yeah. So we wouldn't have any acceleration this way, but we have an acceleration that way because we have a point where our velocity is 0 and then a point where our velocity is something else than 0. We know we have a change in velocity in that direction. Okay, so this relates to the circle because we can take this circle and what we're going to do is just really shrink down the time. We're going to go a time of, let's say, 1,000th of a second. Okay, so, and we're going to say that in a 1,000th of a second, we're going to get to that point, and we're going to cover some sort of angle. So if we can go 1 radian per second, we can go 1 divided by 1,000. So we can go 0.001 radians in 1 second. Sorry. We can go 0.001 radians in 0.001 seconds. Alright, hell yeah. I'm trying to figure out what's the best way to teach this. Because let's say you just, in 1 second, you went 1 radian. You know what I mean? And you should have been here, but now you're there. And you're trying to figure out, well, what's this distance that way? Even though this distance this way isn't radial, we'll get to that. Because if we really chisel down this angle to like a really tiny angle and a very small change in time, then, you know, instead of this becoming an arc and this going straight up, these really turn into straight lines. And then if you have this angle, then this comes down. This is your cosine of the angle times the radius. And this whole thing is just the radius. So then the difference between these two is just the radius minus the radius cosine of that angle. And then you find that distance. You know what I mean? And in this tiny case, you went this distance in that change in time. So the definition of velocity here is, the definition of average velocity. You know, to cover that distance, the average velocity is going to be r minus r cosine theta divided by that change in time, which is real small, so we could do that. So we're going to figure out, hey, if we throw in this time, we're going to get that real small angle. We're going to throw that real small angle in there to get that small distance. And we're going to cover that small distance in that small time again. So the time shows up twice. Time showed up here once. You know what I mean? We already took our omega divided by time. And then we did distance. That helped us get that omega, which chiseled out that distance we're traveling, and then we divide by time again. Okay, so once we do that, this is the average velocity to cover that distance. So we'll do it here. Let's say this is 1 radian. So we have an angle of 1 radian, and we do this in 1 second. We get to here in 1 second, but like we're saying, if we're not around a circle, we just want to move tangentially. We got to there. And so right here, our velocity is 0 towards the radius. There's 0, and I guess you would call it normal, but 0 radial velocity. Our velocity tangential is 1 radian per second times 1 meter. It's radians per second times the something normal, the radius. Radians times radius is something normal. I mean, I'm sorry, it's radians times radius is something normal, and that's velocity tangential. Okay, sweet. So because we have this difference, because we have 0 here, and we have 0 velocity towards the radius here, but we got over there. You know what I mean? And so that goes back to the beginning of the video. Is just like if you see someone there, and then you know what I mean, you see someone there. If they're made of mass, quantum physics superposition doesn't apply. Anything bizarre, and so you know that there's a change in time element. And if there's an observable distance, a measurable distance, and a known change in time, you can find velocity average. Now this is what you start with. You got to start with velocity average. Do that one, and then go back and assess. Well, what was their velocity right here? Was it 0? You know what I mean? And then what was if their velocity was 0 here, and then they moved at a constant speed to get there. That's what we're assuming. Linear speed to get there, or a constant change in velocity to get there. Then we can find this V max. And once we do that, we can know the change in velocity. Change in velocity, well, in this case, is just the max at that point. So V max. And then that's change in velocity. We already know our change in time component, so we can find acceleration. So now we have a definition of acceleration radially or towards the radius. And that's going to be that r omega squared. So that's kind of what we're shooting for. And we're saying our radius is 1. We're also saying our omega is 1. So at the end of the day, we should get something like 1. You know what I mean? And just the absolute value. I'm going to stick with the absolute values. We can worry about that negative later. But the acceleration is towards the radius. And so we should get 1. So let's do it with this one. We're not going to get 1 because we're saying that our angle is pretty big. A radian of 1 in 1 second. And what's this distance right here? This distance right here is our radius, which is 1. It's going to be 1 cosine of 1 radian. So I gotta change my calculator to radians. It is, and we got 1 cosine 1. So this distance right here is 0.54. And yeah, is that what we would expect? Because if we had a 30-degree angle and this was 1, this would be 0.5. If we have a 60-degree angle, it's kind of the exact opposite. This is 0.5 and this is 0.866. Okay, so that's what we see. We got distance 0.54. Now the distance we would travel laterally would be 1 minus that. It would be the radius minus that r cosine theta, what we just solved for. Okay, so now we know that our distance traveled, we'll store that as d, was 0.459 meters. And we're saying in 1 second we got from here to there. That means in 1 second it took 1 second to go this distance. You know what I mean? From there to there, from there to there. And so our velocity average Alright, so for our velocity average in this case is the meters per second. It's that distance times 1 second. So it's basically just 0.459 meters per second. And now we do the definition of velocity average. You know what I mean? Or you can just say, well, if we were 0 here and our velocity average was 0.49, you know what I mean? Our max has to be double that. Because if our max is double this times 2, then the velocity average is 0 plus that divided by 2. And that's our velocity average. Cool. So now that we know that we have a velocity towards the radius of 0.199. Hell yeah. So that's our velocity radial at this point. That's V max. Our velocity towards the radius at this point was 0. We're not going towards the radius. So then we know we have a change in velocity towards that radius of, 0.919 minus 0. And so that's going to be our change, 0.919. And it took, and change in time, that's the definition of acceleration towards the radius. And we get 0.919. So now we're going to do that same process just with our calculator with a really tiny, and let's not get too tiny. Well, let's do tenth of a second. So in a tenth of a second, we're going to go a tenth of a radian. And if we go, I'm sorry. If we're going one radian per second, in a tenth of a second, we're going to go a tenth of a radian. And I think we just said that. So our angle is 0.1 radians. You know what I mean? So there you go. 0.1 radians for this one. Our radius is 1, so our distance here is 1 cosine 0.1. Okay, it's 0.995. And then so our distance here is 1 minus that is 0.0049. And it took 1 second to actually cross that distance. So that's going to be our velocity average. Times 2 is our V max, 0.009916. So that was our change in velocity of 0.009, 9 and whatever. And then so our acceleration is change in velocity, change in time. Now our change in time was that 0.1 second for this example. So divided by 0.1. Oh, that didn't work. Wonder where we went wrong. 1 radian per second. So we have 1 radian per 1 second times 0.1 second. So we have 1 times 0.1 is 0.1 radians. 0.1 radians. This cosine distance will be 1 cosine 0.1. And we're in radians. That's this distance. 1 minus this distance. All right, so 1 minus that distance is that. Oh, that's the thing. The time component comes up twice. So it didn't take 1 second to get there. Hell no. No. We covered that distance in a tenth of a second. So the velocity average is the distance that we traveled times the change in time. You know what I mean? And the change in time is 0.1. So we divide by 0.1. There we get that. This is our velocity. That's our velocity average. Our velocity max is 2 times that. So now our change in velocity is this number from what we just said. So now our change in velocity is that. Definition of acceleration is change in velocity, change in time. So now we have that change in velocity divided by that 0.1. Hell yeah. Now we're getting 0.99916. So we're getting very close to 1. Now this is kind of a bad analogy because you're just like, well, it's r omega squared and our r is 1 and our omega is 1. So 1 squared doesn't, it's kind of hard to see that squared term pop out. But we'll at least do this just so we don't make that mistake again, going through this. So our time component is 0.001. Radians per second, so times 1 second. This is our radians. I'm going to store that as my angle. Now I'm going to go 1 cosine of that angle. So this is my distance there. 1 minus that is that tiny distance that's being traveled in. So distance in change in time is being traveled in, so we're going to take that distance divided by 0.001, and now we have our velocity average. And then double that. So this is our change in velocity, but our change in time is that really small thing. So divided by 0.001. And there you go. Our acceleration is very close to 1 now. And yeah, for our problem, we're going to have to deal with the Earth. And so let's see if this makes sense on the Earth. So this is our problem. I'm just, we'll get to it in a second, an hour from now. But anyway, so we have the radius of the Earth is 6.37 times 10 to the 6 meters. Now we have to figure out how fast the Earth rotates in one day. You know, or just one rotation, actually. How much is one rotation? And so it's not 24 hours. It's not even close. You know what I mean? It's not even just like kind of close to 24 hours. It's because of this. It's like if I rotate just like this, cool. You know what I mean? It's going to take, but if I rotate around a circle, see how yeah. Like if you're rotating around a circle, you rotate once. So just the mere fact of going around a circle rotates you once. So in 365 days, the Earth rotates 366 times. And so basically, yeah, every rotation, oh, holy Toledo. Or is it the opposite of that? Man, okay, I'm losing it. So we're just gonna go right to it. But yeah, it takes 20 for one rotation of the Earth. It's 23 hours 56 minutes. So it's like 4 minutes less. So we're gonna type that in. We're gonna go 4.091 plus 56 times 60 plus 23 times 3,600. So this is the time in seconds for the Earth to rotate once. You know what I mean? On average, 24. It wouldn't mess it up if you use 24. Because even this radius of the Earth is all over the place. You know what I mean? This is just a mean radius of the Earth. And so now we have this. Same thing. Radius of the Earth. But we need to find the omega. You know what I mean? The radians per second of the rotation of the Earth. Obviously, this would be like North Pole, and then we're rotating about the equator. We're looking down on the Earth. And radians per second. Well, what's a radian? You know what I mean? So we could say that. How are we gonna do this? Oh yeah. There's 2 pi. There's 2 pi radians in one circle, and so we want to know that. So basically, all we have to do is take one rotation is. Well, there's a lot of ways you could do this. You could be like, well, I mean, didn't we just find that one revolution of the Earth is 86,164.019 seconds. Okay, so that's so you could figure out, and this is just speed, angular speed, or revolutions is also angular speed. So we could be like, hey, we have this many one revolution every second. So that's our angular speed of little bug on here. Let's see. So it would be one revolution per 86,164 seconds, let's say. And then if you wanted to convert this to radians per second, one revolution, 360. I mean, if you want to take the long way around, is 360 degrees. 360 degrees of a circle is 2 pi radians. You know what I mean? But at the end of the day, you could just say one revolution is 2 pi radians. You could already make that assumption. So we already got one revolution in 86,000 seconds. So we could, and you'll see that come out in the wash too, because 360, we could have just done 2 pi radians over this one revolution. But we definitely wanted to make no mistakes, and so we're going to type in 2 pi divided by that time. So 2 pi divided by alpha t, and we get 7.29 times 10 to the negative 5 radians per second. Now, if the Earth was spinning 1 radian per second, it would travel 60 degrees. I mean, it would take 6 seconds to do 1 revolution. It takes 24 hours to do 1 revolution. So this number is very small. And a rate, yeah. So let's change it to degrees. So let's just do it straight up. We have 2 pi radians in 360 degrees. It's always good to do this. A lot of books will just be pi radians in 180 degrees. Hey, that's fine. We just know that, hey, we have half a circle. That's going to be half a revolution. You could do 1/2 revolution is equal to 180 degrees is equal to pi radians. All the same. Okay, so we're gonna store this as alpha w and multiply by 360, divide by 2 pi. Okay, so every second we're going to go 0.004 degrees. That ain't bad. You know what I mean? And you know what I mean? You would multiply by 60. Every second we're going to go 0.25 minutes. You know what I mean? So on like a USGS map, that's how many minutes we're going to be traveling a second. You know what I mean? So multiply by 60, we're going to be going 15 seconds every second. And more on that later. Okay, so we got our angular, we got our omega, our angular velocity. This would be 0.1234 zeros and then 729 radians per second. 1, 2, 3, 4, 5. There you go. Okay, so let's do that same thing. And we're going to take it to that extreme. We're going to do a time of 0.00 thousandths of a second. So in a thousandths of a second, so if we have our omega stored in our calculator as W of radians per second. Alright, so in our calculator, omega is radians per second. We multiply by the time, and this is going to be we can't have it as t, but I'll just say I don't know what I'm gonna do. I'm just gonna say 0.001 seconds. Seconds cancel. This is gonna be radians. So 0.001 alpha t. Cool. So this is whoa alpha t. No alpha w. Sorry. 0.001 times alpha w. So now we have an even smaller number. You know what I mean? So this is that tiny little slice in a thousandth of a second. That's pretty darn fast. We're still going to move some sort of angle when we rotate. And if we take that angle, so now we're going to store that as our theta. We're going to go, and this is the radius of the Earth, alpha r. So we got that. So we're going to go radius of the Earth, cosine of the angle we just found. This is r in our calculator. And so we're going to go alpha r cosine of that angle. Oh, it's so small it just chiseled out the same thing. Oh, that sucks. I think we might have to go for a little bit bigger time. But let's see. Let's see if it's so small the calculator can't register it. Let's not. We got to do at least 1 second. There you go. So our time is going to be 1 second. So now our so alpha w is going to be our alpha angle. You know what I mean? In 1 second, we're going to go that many radians per second. Or that's how many radians we're going to be going. So now we're going to go alpha r cosine of that angle. It's still the same number. Holy Toledo! It's still so small. And then we're going to go alpha r minus that number, and it's absolutely 0. So yeah, we have to boost it up. So let's go let's go to time of 10 seconds. And let's just see until our calculator registers this. Alpha W times 10. And then alpha R cosine of that answer. Okay, finally. So in 10 seconds, we get some sort of difference. Our calculator registers as a difference. Holy Toledo. Yeah, because alpha R cosine of omega. No, was I doing something wrong? Okay. No, I wasn't. But alpha omega times alpha R cosine omega. No, that worked. Whoa. Where were we? At 1 second, we were just fine. Where was I getting confused? So we're going to go alpha R cosine of omega times 0.1. So that doesn't work, but 1 does. Yeah, so we'll do 1 second. You know what I mean? Because it'll make our acceleration term of R omega squared really pop. Because what is our acceleration? We can just do that right now. Our omega is this, and our alpha R is that. So we're going to go alpha R omega squared. We should have an acceleration of 0.0338. You know what I mean? 7. You know, it's just good to do these problems so often that, you know what I mean, you just little check marks on reality. It's like, hey, that rings a bell. You know, this is our the acceleration towards. Now, is that a pretty small number? I mean, because our acceleration of gravity is 9.8. We know what that is. You go cliff jumping, hell yeah, you know what 9.8 is. But now this acceleration of this is pretty dinky. You know what I mean? So this is what it's saying. If you're like in deep space, and then for some reason there's a fixed point, and there's a chord that's the radius of the Earth. And then, for whatever reason, you're floating along, and then you grab that cord. And then when you do, you every 24 hours, you reach the same point. What's the tension in that cord? I mean, it has to do with your mass. So we can just do it right now. F equals ma, you know what I mean? And we just found the acceleration. We know what our mass is, but maybe we don't. So I'm 160 pounds. Divided, there's a 2.2 pounds in a kilogram. That's easy. Don't have to start memorizing numbers. Holy Toledo. But yeah, so we have 72 kilograms, and then we're going to multiply by that acceleration. So yeah, 2.5 pounds. You know what I mean? Yeah, that's what I thought, about 2 pounds. But yeah, 2.5 pounds of tension on that string. So if you want to hold that string for that 24-hour ride, you have to hold on 2.5 pounds, because else you'd just be wanting to go that way. And then people are just like, well, why does it feel like like when you're going around a track and you get pushed to the outside of a car, why does it feel like there's a force that way? Well, there's not a force that way. It's just that there's a continuity that's making you go that way. You wanted to go this way, but now you're not. So this is a good analogy. So let's say you get to the I mean, if you're spinning around the equator. Yeah, this thing's going to get flung off. So you do feel like you're getting flung off the Earth. I mean, that should be standard. You know what I mean? Anything that's spinning wants to fling those chunks of mass off of it. But you weigh enough on Earth just standing there that if you're at the equator is trying to fling you off, but only 2 pounds of force. You know what I mean? So obviously you feel 2.5 pounds less. Which is amazing. I mean, that's a diet plan. Like, literally, that's fascinating. You go to the equator, you're gonna weigh 2.5 pounds less. I mean, you could go to the top of Everest and you'll only weigh like 8 ounces less, just because you're getting farther away from the gravitational pull of the Earth. But I mean, you get to the fastest spinning part of the Earth, you're gonna weigh 2.5 pounds less. You go to the North Pole, you're back to being heavy. but yeah, so that's fascinating. So when you're just standing there and you don't have a rope attached to you, like what you're feeling is just less weight. You know what I mean? You have to sacrifice 2.5 pounds of your weight that's holding you on to enjoy that ride at the equator. You know what I mean? If the Earth, for whatever reason, wanted to spin hella fast, you know what I mean? You might be sacrificing more of your weight. I mean, if something crazy happened, we're just spinning out of control. You could be weightless, or you could be half as. But yeah, you're sacrificing that weight. That force towards that force. The only way, if you're a mass on the outside of a circle, you know what I mean? Like, just theoretically, that doesn't make sense. You know what I mean? It's like, it seems like you would you would just, the circle would go around you, and you would just be like standing outside the merry-go-round. But yeah, so and to get on that ride, you have to have some sort of force towards the center to stay on that ride. You know what I mean? So like, if a kid is hanging onto a merry-go-round, you know what I mean, and is going real fast and is getting flung off, you know what I mean, to enjoy that ride, to keep enjoying that ride, he has to apply a force towards the radius. You know what I mean? In the name of tension, you know, in his arms. Same thing. If you're in deep space and floating along, and you get that string, you know what I mean, you have to hold on with 2.5 pounds of force to enjoy that ride. But yeah, that is kind of the bizarre thing, because like, hey, yeah, things can get flung off circles. And it seems like there's a force in the opposite direction. Yeah, yep. But anyway, the more you look at it, the better. That's one of those things, just like you probably go your whole life and be like, well, you know what I mean? It's just one of those things where it's just like, I don't know. Especially when people are just like, yeah, it seems like there's a fictitious force out there, and you're just like, well, I kind of want to learn more about that. All right, so let's go back to our 1 second. 1 second. All right, holy Toledo. My camera overheated, and man, I want to quit, you know what I mean? I don't want to finish this video, but we will. I guess it just shows the reality of, like, it doesn't show the reality of like learning. I guess this is how your brain would work if you were kind of struggling through things. I mean, most of the time you just shut it off and then just quit and then go do something else. But I guess what I'm learning is more the teaching process. You know what I mean? Like, what are the words I'm using to explain it? And definitely over-explaining, but it definitely just makes everything a slower process. Like, we're already a minute into this. And so anyway, so what we're going to do is finish up this one. And, you know, all this was saying is, hey, there's a force towards the middle. The next one is if we're in an elevator and we have a velocity, a radial velocity, well, we're going to have a force that, I mean, you're going to feel like you're pushed up against the wall. You know what I mean? So in this case, if you were going around a cylinder, it feels like you're being pushed up against the wall. Well, that means if it feels like we're being pushed this way, the force is that direction. So if we're going up an elevator and it feels like we're being pushed up against the back of the elevator, the force is in that direction. The acceleration is in that direction. So we have a tangential acceleration in that direction. Is that right? For this one, I'm not quite sure. Yeah, I hate how physics comes down to like, well, pick a direction. Which direction is it going? I mean, that's maddening. I just want to know. I don't know. But anyway, so and where were we? I think we were. We already found out that the acceleration. So we got that. Yeah, the acceleration. Oh no, we took a huge pause and then we just said, hey, let's just figure it out. So yeah, let's do it. So we were going to do in 1 second, we're going to travel an angle. So omega, this is how many radians per second. So this distance is going to be r cosine omega. And, you know, might as well do every video with the sun is shining. If this is the angle, sun is shining on the sinin. This component's the sinin component. An angle always says, hey, I mean, if you have a right triangle, you always have a hypotenuse. That's always the largest number. And then, so these are just fractions of that number. So we take the largest number times cosine of the angle, and that means we're taking it times a number less than 1. So maybe like 0.999, and that's what we're doing. Sometimes 0.866, you know what I mean? And then obviously it's the cosine, because here's the angle that we chose. Sun is shining on the sinin. That means this is cosine. Cool. So now this distance, oh, and it didn't work again. Oh, yeah. My theta got messed. So there we go. So we got r cosine of this angle. Cool. And then we want to find this distance. So that's this distance. It's really close to the radius of the Earth. You know what I mean? Because we just barely moved. But this distance is something. And so it's the radius of the Earth minus that answer that we just threw, r cosine theta. So that's the equation. I think it's written here somewhere. R cosine theta. Yeah, r minus r cosine theta. Cool. And so we have a distance of 0.017. And this is in meters. So in 1 second, this distance is 0.01. We need to go 0.01. What is that? Times 1,000. 17. It's 17 millimeters. In 1 second, we need to move 17 millimeters towards the center of the Earth to stay on this ride. Cool. So now we need to know that velocity towards the center. I mean, 17 millimeters a second is probably pretty low velocity, but it's something. So here's our distance in meters. So now we just do the same thing. Average velocity is 0.017 meters per second. That means at this point, tangentially, we had no velocity towards the center of the Earth. But in 1 second, just by observation, we must have had some. And so we can find this V max. It's just going to be twice that. Yeah, this is the velocity. Twice that. So we have a velocity max of 0.034. So now we can, definition of acceleration, change in velocity, change in time. So we have that 0.034 divided by that 1 second, divided by 1. Cool. So, cool. We're getting our acceleration of 0.34. It didn't even pop out at me. And so the actual acceleration is 0.0387. And our value is 0.034. And I just can't get it any better unless I went to like Excel or I don't know how many digits Excel will. These TI-84s, there's no function where you're just like, hell yeah, let's go to 100 digits. You know what I mean? I don't care if it takes a little while to process the number. But yeah, especially with angles, it hated small angles. So let's go alpha r cosine omega times 0.1. That doesn't work. 0.5. That works. 0.9. That works. So we could do 0.99. That works. Um, 0.999. Oh, well, I don't think that actually helps us. No, we'd have to go the opposite way. 0.5, 0.2, 0.1. Yeah, 0.1 doesn't work. 0.15 doesn't work. 0.19, 0.18. Yeah, 0.12. I mean, 0.2 works. So if we went 0.2 seconds, radians is this times 0.2. That's basically what we just did. Cool. So now we go alpha r alpha r minus that. All right, so this is our that's our tiny distance that we're traveling. We're traveling that so that's our distance, and our average velocity is that divided by the change in time, which is 0.2. Cool. So now we know, and we're getting closer to our 0.3387. We can kind of see it come out. So that's our max and our change in velocity, but divided by our change in time was 0.2. Whoa, how did we mess that up? So in 0.2 seconds, multiplied by radians per second, and then we're going to store that as our angle. Yeah, I don't think I did this right. So now we're going to go alpha r cosine that angle. That's this larger distance, and then alpha r minus that answer. That's our smaller distance. So we're covering that smaller distance in 0.2 seconds divided by 0.2. This is our average speed. Multiplied by 2. This is our max speed. That's our change. Yeah, I don't think I multiplied by 2 on that last one. So this is our max speed divided by the change in time, 0.2. So we get 0.3387. And that's cool. And that's pretty close. That's exactly what that is. And so we're getting right on. So that is proving that acceleration is r omega squared. I don't use negatives. I just kind of know. I would rather not. Anytime I see a negative, I'm just like, nah, no thanks. And we can figure that out later. Okay, now we are going to do that second component. Okay, so if our acceleration equation, this was the mystery component, this was the other mystery component. If we have a velocity in the radial direction, that's going to give us an acceleration. Usually if you got a velocity, you're like, no, we don't have acceleration. But that was the same thing as we have a tangential velocity, and it's like, why do we have acceleration? That was the whole thing. So that's our second mystery is 2, the velocity, the radial velocity times omega. So let's do that one. So we have 2 velocity of the radius times omega. So now we're going to have an Earth. We're going to be in an elevator. And let's do this one. I'm going to go online and figure out what the fastest elevator is and what's the speed. We want to know that. We want to know that radial velocity. Alright, so we're back, and we found out that the Shanghai Tower, fastest elevator in the world, and it travels, we're going to do it in meters, 20.5 meters per second. So there you go. So we have r dot, which is dr dt, which r is just like your radius. We could call our radius x. If you want to do that, if our radius is x, it's dx dt. You know what I mean? So it's just, we're saying that this is the radial direction. But we are having an omega, and we're going to call it r. And so, but this is our velocity radially. It's going to be 20.5 meters per second. And our omega for the Earth is 0.0000729 radians per second. I have this in my calculator stored as W. And so we can just get the answer, the acceleration, and I guess, well, let's take a step back before we do this. What's happening here is like, hey, as I go up the elevator, I'm here, and then I'm here, okay, and I think I'll go from, and then as we rotate out here, you know what I mean? Hey, the elevator is going to be over here, you know what I mean? And obviously exaggerated, but because the Earth doesn't spin worth a damn. Yeah. So we're instead of being right here and here, you know what I mean? Hell, well, let's do some lines. Okay, we're right here. You know what I mean? So at some time, 0 right here, and then like, hey, 1 second later. Time 1 second, we're right there. Okay, and I don't know, you probably still don't see it, but yeah, we travel the same distance there, cool. We travel the same distance there, cool. But this sideways, you know what I mean? If we're right here traveling around the Earth, yeah, we have a constant speed. So on the surface of the Earth, or at this part of the elevator, yeah, we're just going that speed. But if we hike to the top of a mountain, you know what I mean, near the equator, well, we're going faster. Yep. Well, I just caught myself. Like, if you're standing on top of a building, you don't feel a force up against a wall just because you're spinning faster. You feel like you're more weightless, you know what I mean? Because to actually stay on the ride, we've already done that one. You have to transfer some of your weight, give up some of your weight towards the center of the Earth. I don't think that made sense, but yeah. Yeah, it's weird. It's weird, the whole like getting flung off compared to sticking on. I mean, I guess I just like to know it from a continuity. Like continuity, to stay on a circle, well, you better be moving. You better have a change in velocity towards the center of the Earth. That's how I think about it. It's hard to think about it, what that means with a force. Well, it does say that if you are a mass, you have to have a force on that mass towards the center of the Earth. No. I apologize. Let's go back to that one. You know what I mean? Because we have, this is the, yeah, we're going to take a moment on it. Because this is the biggest hiccup in F equals ma. You have two sides. Like that's like the take-home point of this video is like, this side is what's happening to the mass. It's like, hey, if we see the mass moving towards the center, therefore there must have been a force on that mass. And I honestly, I don't think I even said it right there. But so when we have the circle and we should be going this way, but we're over here and we have some sort of velocity towards the center, we have that change in velocity in the radial direction. That means just in general we will have an acceleration towards the center, and that's going to be negative r negative r omega squared, and we solve that. Okay, so this negative r omega squared is our acceleration. So we can say, hey, F is equal to negative r omega squared. Cool. But now we have to actually do a free body diagram. So if we're on the surface of the Earth, and there's us, and here's our mass, and we do have a weight, we do have an mg down, and then we have a normal force up. You know what I mean? So this was the acceleration, and we have a mass over here. So mass times acceleration. And I guess we're just going to say, hey, this is the y positive direction, this is the x positive direction. So my forces are going to be a normal force up, negative mg down, and I swear if this negative sign doesn't work out, I'm just going to lose my mind. But yeah, we have a negative mr omega squared, and would this make sense? So now if we bring the mass over here, we just want a final normal force. Yes, it does make sense. Now we have an mg, our weight, minus that mr omega squared. So there you go. We are going to feel lighter because the normal force, is basically the scale. The normal force under our feet. I mean, just to hold ourselves. Yeah, and obviously the ground's falling away from us because that's what's happening. We're getting closer to the Earth. We're always moving this way just a little bit, even though the ground's always, like at every time, the ground's always underneath us, but we are just moving towards the center, moving that direction. Cool. And the normal force will be our weight minus that acceleration. So the normal force is going to be lighter by 2.5 pounds. Well, it'll be our weight, mg, minus 2.5, because we already did that part. It's 2.5 pounds. And there you go. Or just 1 kilogram. Yeah, that'd be pretty decent. Yeah, so but yeah, it's good to do that, because we'll probably still have to do the same thing with this block. And let's see if we can do that. This is the struggle. So as we're moving up here, we're traveling a larger distance. See how this distance is larger. And so if we find the omega, well now this is arc length. So that's pretty cool, because we can take the angle in radians. So we can go radians times radius. Well, hell yeah, it gives us something normal. Hey, we get to use arc length. Hell yeah. I haven't done this one in a while. And so we're going 20.5 meters per second. So we're just going to say time is 1 second. Hell yeah. How far up vertically are we going? We're going to go 20.5 meters. So in 1 second, what's our angle? Well, we already have that stored. It's the radians of the Earth is radians per second times 1 second. This is how many radians we're traveling. Radians times radius. So omega r, or the radius alpha r times the angle. So we're going to go 464.5 meters. And that's amazing. You know what I mean? In 1 second, we're going to travel 464.5 meters. You know what I mean? And let's back that up, because is that right? I swear it's like not right, but this is in radians per second times radius gives you arc length. Is that right? So radians per second, we're saying a time of 1 second. And I don't think I changed W at all. That looks still the same. And the radius of the Earth hasn't changed. 464 meters. It just seems... well, yeah, I always thought we were going 1 mile... Yeah, I thought we were going 1 mile a second. But no, yeah, isn't that right? Because in 1 hour... Let's just do this. In 1 hour, you can travel across a whole time zone. And at the equator, it's 1,000 miles. So you're going 1,000 miles an hour. That's a really good thing to keep in the back of your mind. 1,000 miles an hour at the equator. And up here in Montana, we're going like 700 miles an hour. Miles an hour. Let's figure out how many meters per second. Miles per 1 hour. Miles is 1 mile. Got to cancel. 5,280 feet. We got 1 hour. 3,600 seconds. Cool. Oh no, seconds. So hours. So we're gonna get feet per second. Damn it. And then 1 foot is 12 inches. This is the only way I can do it. And then 1 inch is 25.4 millimeters. For the love of God, I'm sorry. But I got to go from millimeters to meters. 100 millimeters is 1 meter. So yeah, plenty to get messed up on. Or you check on reality. Miles per 1 hour is 5,280. No, that's not going to help. No. 1609 meters. Yeah. 1609 divided by 360 seconds. So this is meters per second. That's a mile, and that's an hour. This is 1 mile per hour. Meters, 1609 divided by 36,000. And if we did this way, 1,000 times 5,280 divided by 3,600 times, sorry. No, we're good. Times 12 times 25.4 divided by 1,000. or maybe I messed up. So we have 1,000 miles times 5,280 feet divided by 3,600 times 12, 12 inches in a foot, times 25.4 millimeters an inch divided by 1,000. So we get, yeah, I probably already had it, 447. Yeah, that's wild. So, yeah, in 1 second, we're going 447 meters. Damn. Okay, fair enough. And why did we even solve that? I swear to God I'm pushing through this. We will do this. Alright, so, yeah, oh, we wanted to do arc length. Yeah, so hell yeah. So we're just going to say, obviously this is going to be the surface of the Earth, you know what I mean, right at the Shanghai. And yeah, so that arc length would be, well, it would be r omega. Cool. And then, what's the arc length here? Well, you have to take the radius of the Earth plus 20.5. You know what I mean? It's like super negligible. But once we take that radius times the radians times alpha w in our calculator, then we'll have something different. So I'm gonna store this as quickly as x, and then so we have alpha r plus 20.5. Sorry, alpha r plus 20.5. Cool. Times the radians. And we get something different. I'm going to store that as alpha y. So now we have alpha y minus x. Whoa. Alpha y minus x. So this arc length minus this arc length. And guess what? We have a difference. Super small. This is why this one's even smaller. Yeah, the 2 pounds. I think it's less than 2 pounds. Even on this fastest elevator in the world. Because what I wanted to do was do this as an amusement park ride. You know what I mean? Go here, go up against the back of the elevator, and then see if I felt any force on my back as I was getting sucked up against the back. And so we definitely need to talk about this, because if I was here, I was just traveling that way. But now, once I get up to here, I had to travel farther, and to do that, the elevator had to push me to make up that ground. So same thing, right here. I have no velocity. My velocity tangential is 0. But if that was the case, when I got to here, even though, like, I would, oh no, that's not true. No, it's not that my velocity is 0. But, oh, this is going to be with the golf ball problem. Holy hell. In this, hell yeah, my velocity that direction is 0. But in this case, my velocity that direction is my tangential velocity. But it's just due to continuity that if I'm moving up this way, in 1 second, I had to travel, like if I'm moving this way, like I didn't have any extra velocity that way, and I had to make up that distance. So if I do this, and I would just get to there, but then I got to make up that distance. So this is the distance that we're making up. And right here, I don't have any effort that direction. But due to continuity, I had to be over there. And then this, I'm going to store this as d. So this is the distance that we traveled in 1 second. So again, my average velocity that direction, divided by 1, that was my average velocity, multiplied by 2, that is my max velocity once I get to this point. And then so divide by max velocity, or velocity change in velocity is that velocity max, which is 2 times velocity average, and then I was 0 here, so that's my change in velocity, divided by change in time, that's acceleration, and we get, and this change in time was 1. So this is our tangential acceleration due to that speed. And so now we can just throw it in. We can go 20 point, and then we're going to store this as alpha A just so we don't forget about it. So we're going to go 20.5 meters per second, that was our speed, times omega, the radians per second of the Earth, times 2. And hell yeah, you get the same, you get exactly the same number. So, and it's 0.00, like what would we get for the other one? We got point, it's not even on here? Come on, I had to write it down at least like once. Maybe not on that sheet of paper though. Yeah, didn't we do it? Well, I mean, we just do it, just r omega squared. R omega squared. 0.03. So yeah, so this acceleration is potatoes. Let's see, compared to the acceleration of 0.0029. So we got 0.003 compared to 0.03. And obviously you could have a faster elevator. I mean, the rotation of the Earth is pretty fixed, but this, we're talking about going up something real fast. You know what I mean? A fast elevator, or like an amusement park ride that shoots you straight up. You know, that would be a better one probably, because you might be able to get 20.5 meters per second. And I usually do this as just 20.5 times 2.25. I call it 20.5 times 2, you know, plus a 25% tip. So 20.5 times 2.25. Yeah, we got a speed of 46 miles per hour. So I just don't know if you could create an amusement park ride where you actually have a velocity of like 100 miles an hour in a vertical direction, and it's only going to be, you double this number, it's only going to double your acceleration. So now let's go back to F equals ma. We have 160 divided by 2.2. So yeah, we have, let's just do 70 kilograms of mass times, well, I want to do it right, 72 kilograms times our acceleration. Oh, did I store it? Yeah. So that times our acceleration. So we have a force of 0.2. Oh, and damn it. That's why. That's why I got confused. The acceleration at the equator was 2.5. I said it was pounds. Hell no, that's newtons. So my apologies. That's the hardest thing about being, you know, engineer in America, because man, you're just used to pounds and stuff. But yeah, 2.5 newtons is 4 newtons to a pound. So you only weigh like you weigh half pound less. You know, that's what I thought. And then I think even on top of Everest, you'll weigh a half pound less. So you could either go to the top of Everest, and those would be about the same. And like you want to do that one? Yeah, it would be like, compared to, how would that work out? Oh, no. It'd be like, if you were on the, Everest is like, so if you're on the North Pole, you know what I mean, and let's say that everything's the same radius, and then you just went to the top of Everest. Well, gravitation isn't as strong on Everest. But what we're talking about is going to the equator and spinning and trying to get flown off the Earth. That's going to be a half a pound. The one on Everest, and we can do that, is, you know, force is equal to mass times acceleration. The force is gravitational constant, m1, m2, times radius squared. And I think the mass, the gravitational constant, 6.67 times 10 to the negative 11. Hell yeah, that's a good one to memorize. And there's a way to do that. I'm not going to go over that right now. Mass of the Earth is 5.94. It's usually 6 times 10 to the 24. 6 times 10 to the 24. There's ways to memorize that, but I'm not going to go over that right now. And so there you go. and then the masses cancel, so we just need to figure out our acceleration. So at this point, then you figure out your acceleration, from that, and then you go back to, this is the acceleration of gravity, and then you would go back to putting yourself on top of Everest, and then you would have mg down, and then you would have a and that's it. So what you're comparing is the r. You're comparing just the radius of the Earth plus compared to the radius of the Earth plus Everest, which isn't that at Alright, so I looked up the height of Everest, and we have 8,850 meters. And so let's go back to our F equals ma equation, and we have g m1 m2 radius of the Earth squared. That's going to be our mass one, us. And so we just want to know the acceleration of gravity. And cool. And then so we're going to get the acceleration of gravity, which is g m2 r squared. G is 6.67 times 10 to the negative 11. Mass of the Earth is 5.94 times 10 to the 24. And okay, so I'm going to 5.94 times 10 to the 24, we're going to store that as alpha m. 6.67 times 10 to the negative 11, store that as alpha g, and away we go. So we're going to alpha g, alpha m, divided by, so we got the radius of the Earth squared. This is going to be, and it comes in just a little bit lower, but it's 9.76. I guess it rounds to 9.8. So we're going to store that as alpha c, just for now, and then we're going to come back here, and now we're going to do let's do it. We're going to go alpha g, alpha m, divided by, now we're going to have the radius of the Earth plus this height of Everest, 8,850, and then we're going to square that. So now we're going to have a new acceleration, and that's going to be 9.74, let's say. Okay, so now the difference in the acceleration, we could just do that. We could just say the force, the change in force that I would feel is just going to be my mass, 72, times c minus b. So we're going to go alpha c minus alpha b. And this is going to be an acceleration difference of 0.072. And that's significant because 0.03 was the spin of the Earth. You know what I mean? And so, hell yeah. You go to Everest, you weigh 8 ounces less. Yeah, and I kept getting confused between 2 pounds. It'd be cool if your weight loss diet would be go to the equator, weigh 2 pounds less. I mean, that you would advertise that. You know what I mean? Fly to the equator. You know, weigh 2 pounds less. Hell yeah. That's noticeable. That's noticeable. The other thing that I want to do, because you can get higher than Everest, because Everest is only at 29,000 feet. Well, I don't know if you can get too much higher. Like how high do planes fly? I thought they flew at 35,000. You know, so you could actually do this yourself, though. Weigh yourself. I've definitely, next time I fly, I haven't flown in a long time. Next time I fly, though, I want to bring a scale. Hopefully it passes through everything. But then, waiting to board my plane, hop on the scale. Or even just, in the aisle, hop on the scale. And then at 35,000, get out of my seat, hop on the scale. And as long as I didn't, get dehydrated or eat any snacks or drinks or anything, hell yeah, I should be able to noticeably weigh 8 ounces. I would want to bring a good scale, probably a digital one that was reliable. But anyway, so let's go back to here. And so 160 divided by 2.2 times that acceleration. And we weigh 1.96 newtons, and again, divided by 4.44. So it's 0.4 pounds times 16, 7 ounces. You know what I mean? So if you go hike to the top of Everest, you'll weigh 7 ounces less than at the equator. So now we can go back to probably our original problem. We already found it though. I don't know where I stored it though. 0.029. 0.0029. And times 160 divided by 2.2. That's so this elevator ride, you would feel 0.2 newton. And I kept saying pounds. I apologize. That's a huge typo. I'll get better. But 0.2 newtons divided by 4.44. So it's 0.05 pounds. What the hell is that? Times 16. It's less than an ounce. So, you know what I mean? So going up this elevator, if you had your back to the wall, it would be less than an ounce. And it's not even worthwhile, you know. This elevator, the latitude is at 30 degrees. So I looked that up and printed out a sheet, but you know what I mean. At this point, who cares? Because it's not even worth, you know. Yeah, so the latitude is 30 degrees. So I mean, if we take this and we're going to 30, well, that's significant. Like this radius is much smaller. And that doesn't help things. I mean, you're going slower. Same distance, but you know, shorter distance, longer time. So yeah, that's the opposite of fast. And yeah, so the you know, that omega would be lower. And so that one, and yeah, it's too bad because I wanted to actually experience that type of acceleration. You know what I mean? Because it is part of the equation, and it's one of those mystery ones. It's just like you have to have something, you know, with the velocity that way, and then spinning at the same time. But heck yeah, does that do it? I mean, that's in a nutshell. The crazy thing is, I don't think I learned a damn thing. You know what I mean? I've already known all those things. I just redid them for a video that wasn't very good. And so now we still want to try to tackle this problem. And I don't know. Yeah, so I guess let's just read it. So the air resistance is negligible. And for me, it's like I consider that a vacuum. You know what I mean? So, yeah, it's just a vacuum. So the second something leaves, like, is that the case? Like, that was just the bizarre thing. Is like, if the Earth is spinning underneath you, and then you throw up a ball at the equator, in a vacuum, when it lands, well, now how does this work out? No, because we're already saying you and the ball already have that tangential velocity. But that's all you'll have. So the second you throw it, no, it still doesn't make sense. Is because it's up there, I really have to, some of these problems you really have to take to the extreme. Where if the Earth looks like this, and I was able to throw something up like 3 times the diameter of the Earth, and then it fell back down, and the Earth is going to rotate and the Earth is going to rotate to here. So this point's going to go to there. 1 goes to 1, and then 2 goes to 2. Now the question, does this ball land over here? You know what I mean? Like, is it physically? I mean, so and maybe this is a horrible picture, but so the ball has a velocity that way, tangential. The Earth has a tangential velocity, so those are going to be the same. Does it take a longer path because it goes up here, like radially? If it, like, let's just say instantaneously it was up there. So if I could throw this ball and get it up there as high as possible in such a fraction of a time, it wouldn't matter. And then after some time, it comes back down to Earth. And then I'm going to say this ball only has a velocity to go that far. And then, so here's the example, because I usually, I have to take a problem and take it to, some extremes that make sense. And so this is what I'm going to say. I can throw a ball up instantaneously. Same thing as, shooting a gun straight up in the air. But then, for whatever reason, I'm just going to say it instantaneously gets up to here, but still has this velocity. And we're going to say in 1 second... and then in 1 second it moves from there. We know that because that's all the velocity it has. And then all of a sudden, the next instant, it comes straight down to Earth. But then the Earth in 1 second can get to there. So it's going to lag behind. That's the only analogy. I think that makes sense to me. Now, we know that this ball can't get up there instantaneously, but we have just proved, I think, that if it's up there, then it would have to take a longer path. Because in this example, well, if the Earth wasn't moving, it would have to go up and then down. So we know, and let's say that takes 1 second. You know what I mean? So it goes up in a half a second and then down in a half a second. And but when the Earth is spinning, it does have a velocity that way, and we know its velocity is just that much because in 1 second the Earth would be there. You know what I mean? So this component's way bigger. You know what I mean? In 1 second, it can go up and down. So this is real fast. Or is that right? Real fast. And then this is how fast the Earth can go. You know, the Earth is rotating that. And so the path in a half a second to get up there, well, you would move that far. So by the time you're going up, you're going to move to there, and by the time you move back down, you could move the other half. Huh. Yeah. I mean, even that. See, I'm trying to take these problems to extremes where it's just you can rule out, not knowing anything. Where you're just no, I can totally 100% agree with that statement. But even that, I still don't see it. Okay, well, moving on. Okay, so you tee off from 35 degrees right there. And you hit a ball south, and that's what they're saying. It's alright, that's a bummer. My camera cut out, and so, we're just going to start this one over, because if I just publish it as a video from scratch, I think I can just start from here. So, hell yeah, let's do it.